Imagine, if you will, standing at the fore of a technological revolution, where machines learn and innovate alongside humans. Picture yourself as the architect behind these intelligent systems, shaping the future of industries from healthcare to finance, from autonomous vehicles to space exploration. No, this isn't science fiction. It's the reality of AI and machine learning, and you're about to embark on a journey to master it. Welcome to the AIML Engineering Advanced Professional Certificate Program. Whether you're just starting your journey into AIML or looking to deepen your expertise, this program is designed to equip you with the skills you need to excel in the world of artificial intelligence and machine learning. In this video, you'll learn what to expect from this program, how the program is structured, and which skills you'll walk away with upon completion of the program. This comprehensive program covers the full spectrum of AI/ML engineering, from foundational concepts all the way to advanced techniques. You'll dive deep into essential areas like supervised and unsupervised learning, deep learning, reinforcement learning, and AI model deployment. But that's not all. We also cover real-world applications, so you'll gain practical skills you can immediately put to use. The program is structured to provide a balance between theory and hands-on experience. You'll not only learn how algorithms work, but you'll also get plenty of opportunities to practice building, training, and deploying models. Each module includes projects and labs that are designed to simulate real-world business challenges, giving you the chance to apply your skills in meaningful ways. AI and machine learning are transforming industries around the world, and the demand for AI/ML engineers is skyrocketing. From healthcare and finance to retail and autonomous systems, AI is reshaping how we work, interact, and make decisions. With this certificate, you'll be well prepared to take advantage of these growing opportunities and become a key player in this evolving, exciting field. By the end of this program, you'll have developed a solid portfolio showcasing your AI/ML expertise. You'll know how to build and deploy machine learning models, fine-tune deep learning networks, and create end-to-end AI solutions that are both scalable and efficient. Whether you're aiming for a role as an AI engineer, data scientist, or ML researcher, this certificate will give you the tools and confidence to take your career to the next level. The future of AI and machine learning is unfolding right now, and you have the opportunity to be at its fore. So here's our challenge to you. Take the initial step of your learning journey by completing the first lesson of this course today. Then commit to regular learning sessions each week. We're excited to have you on board, and we can't wait to see the incredible projects you'll build throughout this journey. Thank you, and welcome again to the AI/ML Engineering Advanced Professional Certificate Program. Have you ever wondered how AI systems learn to specialize in solving specific tasks, like translating languages or generating code? Imagine a customer service chatbot that not only answers questions, but understands cultural nuance and adapts its tone perfectly for each customer. Or picture an AI writing assistant that can seamlessly switch between technical documentation and creative storytelling. This level of specialized AI performance is possible through fine-tuning large language models. In this course, we'll unlock the secrets behind customizing LLMs for real-world applications. By the end of this course, you'll be able to define, describe, and design the architecture of an intelligent troubleshooting agent. You'll be able to implement natural language processing techniques for user interaction. You'll be able to develop decision-making algorithms for problem diagnoses and resolution. You'll also be able to optimize and evaluate the performance of AI-based troubleshooting agents. In this course, we'll introduce the fascinating world of large language models and how fine-tuning them can transform AI from a general-purpose tool into a highly specialized assistant. Fine-tuning allows models to adapt to specific tasks, such as customer service or content generation, making them indispensable for businesses looking to improve efficiency and performance. We'll take a closer look at how fine-tuning works by modifying existing knowledge within the model to suit particular applications. Think of an LLM as a library of knowledge. With fine-tuning, you're directing the model to focus on certain sections of that library, depending on the task at hand. For example, you can train a general-purpose model to specialize in processing legal documents or to understand medical terminology, unlocking its potential in niche sectors. We'll also touch upon the technical aspects of fine-tuning, such as adjusting hyperparameters and selecting training datasets that are aligned with your intended task. By understanding these foundational steps, you'll see how fine-tuning elevates AI from being a basic tool to becoming a targeted solution tailored to your exact needs. Additionally, we'll explore practical examples of fine-tuned models in action, from enhancing search engines to automating customer interactions. This includes how companies like Microsoft and Google have successfully fine-tuned models to improve product recommendations, personalize user experiences, and even increase the accuracy of virtual assistants like Cortana or Google Assistant. Through this course, you'll gain a deep understanding of the techniques used to fine-tune LLMs, ensuring they can be deployed effectively in real-world scenarios. By diving into the specifics of how to fine-tune LLMs for different tasks, you'll develop the skills to make AI a valuable tool in your toolkit. Whether you're working in finance, healthcare, or any other industry, mastering this skill will make you a valuable asset in today's data-driven world. If you're ready to take your AI skills to the next level, I encourage you to reflect on where you could apply a fine-tuned LLM in your own projects. What business challenges could you solve with this powerful technology at your disposal? Did you know that a pre-trained language model is like a raw tool waiting to be sharpened? Fine-tuning is the process that transforms it into a precise, task-specific asset capable of handling specialized tasks with accuracy. In this video, we'll explore why fine-tuning is the key to unlocking the full potential of AI and how you can apply it to solve complex problems in your field. You'll learn how fine-tuning makes AI models smarter and more efficient, so you can leverage this powerful process to improve your own projects. By the end of this video, you'll be able to explain why fine-tuning is essential for LLM performance. You'll be able to identify real-world use cases where fine-tuning makes a difference. Finally, you'll be able to recognize the benefits of fine-tuning in specialized tasks. Fine-tuning large language models, or LLMs, is one of the most impactful ways to ensure that they can perform specific tasks with high accuracy. While LLMs are pre-trained on vast amounts of general data, fine-tuning narrows the model's focus, enabling it to excel in specialized areas. Imagine trying to use a basic, unspecialized AI to translate complex legal documents or diagnose medical conditions. Without fine-tuning, the results would likely be inaccurate or incomplete. Fine-tuning allows companies and developers to mold these general-purpose models into highly efficient, task-specific tools. Fine-tuning involves retraining a pre-trained model with a smaller, more targeted data set that aligns with the specific tasks the model will be asked to perform. For example, a healthcare provider may fine-tune a model to understand medical terminology, or a retail company may fine-tune a model to improve product recommendations. So what are the benefits of fine-tuning in real-world applications? One example is how virtual assistants, such as Microsoft's Cortana, rely on fine-tuning to adapt to various industries, from customer support to legal advising. This ability to customize a model to meet specific needs increases accuracy, improves efficiency, and ultimately leads to improved user satisfaction. Moreover, fine-tuning enables the use of smaller data sets for specific tasks, reducing the need for enormous computational power, which is typically required for training models from scratch. This makes it a practical and cost-effective solution for businesses of all sizes, allowing them to deploy AI in targeted ways. To summarize, fine-tuning transforms pre-trained models into specialized tools that perform tasks with precision. Knowing this, you'll explore the technical process of how to fine-tune a model and ensure its effectiveness in real-world scenarios. Now, it's your turn to harness the power of fine-tuning. Identify one or two specific tasks in your industry where fine-tuning AI models could enhance accuracy and efficiency, and consider how you can apply this process to solve complex challenges in your field.
Think of Git as your project's safety net. It keeps track of every change, every addition, and even every mistake, allowing you to go back in time or collaborate seamlessly with others. In this video, we're going to show you how to set up a Git repository for your machine learning project so you can code with confidence and keep everything under control. By the end of this video, you'll be able to create and set up a Git repository for your project, and organize your files and structure your repository. Let's begin by initializing a Git repository for the project. Let's go to Notebooks, and let's create a new folder where the Git repository can live. I'll create a new folder, and I will name it Git Test. You can name the folder whatever you'd like. Now within Git Test, I'll right-click and create a new file. I'll call it untitled.ipynb, leave it as is, and create the new Jupyter notebook. Let's add a line here. And then save the file using Control-S. Now, let's click on the menu at the top left of the notebook panel. Then click Compute, then click Open Terminal. This option will be grayed out for you if your compute instance is not active. In that case, make sure to start your compute instance, wait for it to finish starting, and come back to this menu. Now, within the folder we've just created, run the command git init, I-N-I-T, and press Enter. By initializing a repository, we can now track changes and create a history of the development process, making it easy to collaborate and revert changes if needed. Now, let's stage our files for commit and make our first commit with a meaningful message. Committing code is a crucial part of version control. First, we will stage all files in this folder using git add space period, and then press Enter. You may get an error message calling out dubious ownership. This is because our directory does not exist on the compute instance itself, but elsewhere in Azure, and is simply mounted to our compute instance. Run the command listed below to add an exception, then run git add period again. I will copy the command using Control-C, then press Control-V and Enter to run the command. Then I will press the up arrow twice to bring up the git add command that I ran earlier, and press Enter. Now, let's commit the staged files with a clear descriptive message using git commit-m. I will say git commit-m, and then in quotes, initial commit. And then press Enter. If this is your first time using Git on this compute instance, or you don't have Git set up globally, you'll need to configure your email address and name. Do so using the provided commands, then run git commit again. I'll copy the first command using Control-C and Control-V to paste it. Before I press enter though, I will replace it with my email and then press enter. I will do the same for my name. Now that I've configured my email and name, I will try to commit the message again. And this time my commit goes through. In this video, you've set up and managed a Git repository for your machine learning project. You saw how to initialize a repository, organize files into a clean structure, and commit changes. Now it's time to put this knowledge into action. Create a Git repository for your own machine learning project, organize your files, and commit changes. Imagine losing hours of work because a bug you can't track down overwrote crucial code, or worse, because you accidentally deleted it. In this video, I'll show you how to go from local commit to full remote setup on GitHub, all the way to setting up branches for safe, efficient development. Let's dive in and make sure your hard work is protected and versioned right from the start. By the end of this video, you'll be able to commit your code with meaningful messages, push your repository to GitHub, and set up branches for effective version control in collaborative and ongoing development. Committing your code with meaningful messages ensures that every change you make is recorded, making it easier to track progress and roll back if necessary. Once we've committed the changes locally, it's time to push the repository to a remote platform such as GitHub. This makes your code accessible and backed up in the cloud. We'll create a new repository on GitHub using their web interface. Open a new tab and go to github.com and sign in or sign up for a new account. I'll create a new repository with the same name as my directory in Azure. I'll call it git test. You can use a different name, but using the same name simplifies things. Then I will click Create a new repository, making sure to keep it private. Then I will click HTTPS here and copy this URL. I will go back to my terminal and type git remote add origin space and then paste the URL I just copied. Now we need to authenticate with GitHub. Visit this link. The link will be provided for you to access the script to set up the GitHub CLI. I've copied this link and I'm pasting it in a new tab. You can also pause the video here to copy the link manually, to type the link out manually in your web browser and visit it. Here, I will copy the install script for Linux, since our compute instance runs Linux, and paste it in the terminal, then press enter to run it. When the script finishes, I will type gh space auth space login and then press enter. I will select github.com. Github.com is already selected, so I will press enter. I want to connect over HTTPS, so I will press enter. And I want to log in with a web browser, so I will press enter. Now, let's click this link to open the GitHub authentication in a new tab. I will continue to sign in as Coursera AIML. I will continue to sign in to my GitHub account. Then I will go back to the terminal and copy the one-time code to paste into my web browser. Then I will click Continue. Then I will click Authorize GitHub. I will re-enter my password to confirm. And now my device is connected. Back in the terminal, I will press Enter, which will attempt to open the link in a web browser, but since there is no web browser on this compute instance, the attempt to open the browser will fail. However, the attempt to authenticate will succeed, and we have now logged in as Coursera AIML to our GitHub account. Now we will push the code to GitHub using git space push space dash u space origin space master, making sure to spell origin correctly, and then press enter. Finally, we'll set up version control for ongoing development using branches. Branching allows us to work on new features without affecting the main codebase until changes are ready. Check out a new branch for development using git checkout -b. Make sure that you have supplied a name for your new branch. Let's call this feature-branch. Then press enter. Now, let's make some changes to our Jupyter notebook. Let's say Git is a very useful tool. And then press Ctrl S to save our notebook. Returning to the terminal, we will do git space add space dot to add any new files that may have been created. Then we will type git commit space -m space and then our commit message, which in this case will be added details on Git to the Jupyter notebook, and close with a quote and press enter. Now, we will return to the master branch using git checkout master, and then merge our branch using git space merge space feature dash branch, and then press enter. Using branches allows for parallel development. You can test new features, fix bugs, or make updates without affecting the stable version of the project until everything is ready. In this video, we covered the basics of using Git and GitHub to manage and protect your code. You learned how to commit with clear messages, push your work to a new GitHub repository, and set up branches for safe, organized development. Now, you have the tools to track changes, collaborate, and ensure a stable project. Try it yourself. Set up a GitHub repo, commit with clear messages, and create a branch for new features. Ever wonder how data selection impacts the performance of a fine-tuned model? In this demonstration, you'll see a real-world example of selecting and preparing data for fine-tuning, showing how critical it is to get this process right. By the end of this video, you'll be able to decide how to select task-specific data for fine-tuning, pre-process the data and prepare it for training, apply key principles to ensure balanced and high-quality data, and implement Python scripts to replicate the process for your own model. In this demonstration, you'll be guided step-by-step through a real-world use case where an organization fine-tunes a large language model for sentiment analysis of tweets, as posts on the platform formerly known as Twitter were called. you'll see code snippets to help you replicate the process. Let's start by making a new Jupyter notebook. I've already created one, and I've called it Preparing for Fine-tuning. I'll make sure to select the correct kernel in Azure ML, that is Python 3.8 Azure ML, and then we can start running Python code. Let's begin by defining the task. The task is the sentiment analysis of tweets to classify responses, to classify tweets as having a low, medium, or high intensity of emotions. We'll use a dataset of tweets and collect and organize the data. First, we will install any extra modules we need. In Jupyter Notebooks, an exclamation point before a line means to execute that line on the system instead of with the Python kernel. This will run pip install NLTK. Then we will import the necessary libraries, load our dataset, and print the data. I press Control-Enter to automatically run the code in this Jupyter Notebook code block. Next step is data pre-processing. Once the data is collected, we must clean and pre-process it. This includes text cleaning, removing irrelevant information, special characters, and standardizing the text, for example, by converting all text to lowercase, and tokenization. Using the appropriate tokenizer for the pre-trained model, we will split the text into smaller units for efficient processing. In this case, we'll use a tokenizer compatible with the BERT model. We will start by defining a function to clean text that will, for example, remove all the text in square brackets, remove any URLs in the tweets, remove any HTML tags that might have snuck through to the dataset, and remove all non-alphabetic characters. It will also convert all the text to lowercase. Then we will apply this clean text function, and then using the BERT tokenizer, we will tokenize the data. The next step is data splitting and class balancing. We will split the dataset into training, validation, and test sets. We will make sure the data is properly balanced between the different sentiment classes. Oversampling or undersampling can help achieve class balance, ensuring the model doesn't become biased towards the majority class. Here, we will import train test split from scikit-learn, and then we will initially create a 30% split for the validation and test sets, and further split that 30% into the 15% validation set and the 15% test set. Next, we will cover augmentation techniques. In some cases, data augmentation techniques, such as paraphrasing or synonym replacement, can increase the diversity of training examples. This can be especially helpful in smaller datasets to improve model robustness. Here, we will use NLTK to download WordNet and then import it. We will define a function that replaces a word with a synonym that is a similar word. Then we will apply this synonym replacement on the whole dataset and apply the augmentation. Finally, we prepare the data for use in the fine-tuning process, ensuring that it's structured and formatted in a way that the model can process efficiently. First, we convert the inputs and labels into PyTorch tensors. Then we define a mapping function, mapping the sentiments listed in our dataset from high to 1, from medium intensity to 0.5, and low emotional intensity to 0. Then we will apply the function to each item in our sentiment intensity dataset. We will drop any rows where the sentiment intensity is none and convert sentiment intensity to a tensor. Then we will create a data loader for training. In this video, you walked through the process of selecting and preparing data for fine-tuning using a large language model, or LLM. Using a real-world example of sentiment analysis for tweets, you learned how to define a task, select task-specific data, clean and pre-process the dataset, and split the data into training, validation, and test sets while ensuring class balance. We also touched on techniques like data augmentation to enhance dataset diversity. By the end, you gained an understanding of how crucial data selection and preparation are to the success of fine-tuning process, setting the foundation for your model to excel in specialized tasks. Now that you've seen how data impacts fine-tuning, think about your own projects. How can you ensure the data you're working with is high quality and ready for training? Try using these code snippets to replicate the process with your own data. Have you ever wondered how to turn raw data into something your machine learning model can use? In this step-by-step walkthrough, we'll show you how to take unstructured text data, clean it up, and prepare it for fine-tuning, turning it into a powerful asset for your AI projects. By the end of this video, you'll have the skills to efficiently pre-process your own data, ensuring it's ready for training and optimized for success in real-world tasks. By the end of this video, you'll be able to collect and organize raw data for fine-tuning, clean, pre-process, and tokenize your dataset, and structure your data in a format ready for model fine-tuning. Let's begin by creating a new Jupyter notebook. I will call this Preparing for Fine-Tuning. Then I will make sure I have the appropriate Python kernel selected. Step 1 is to import your dataset. You should have already downloaded the Tweet Emotion Intensity dataset from Hugging Face. Here, we will import that file and print out the first few lines of it. Step 2 is to clean the text. This step is cleaning the raw text to remove unnecessary characters, such as URLs, special symbols, or HTML tags, and to normalize the text by converting it to lowercase. Here, we define a function to clean the text that removes any URLs, any HTML tags, and any punctuation from the text. It also converts all the text to lowercase to normalize it. Then, we make a new column called cleaned text that is equal to the data in the tweet column that has had this clean text function applied to it. Step 3 is to handle missing data. We now handle missing or incomplete data in your dataset. You can either remove rows with missing data or fill them with placeholders, ensuring the dataset is complete for training. We can see that there was no missing data in this dataset, so let's move on to the next step. Step 4 is tokenization. After cleaning the text, we tokenize it. Tokenization splits the text into individual words or subwords that can be used by the model. We'll use the BERT tokenizer to ensure compatibility with the pre-trained model you are fine-tuning. Here, we load the BERT tokenizer from the transformers library from Hugging Face, and then we tokenize the cleaned text that we defined earlier. Then we will print the tokens of the input IDs, and you can see them here. The words have been converted into these numbered tokens. Step 5 is to structure the data for fine-tuning. With the text cleaned and tokenized, we will now structure the dataset for fine-tuning. Here, we will import Torch and Tensor Dataset and Data Loader. We will convert the tokens into PyTorch tensors. we will define a mapping function that sets the tweet sentiment intensity from high to 1, from medium to 0.5, and from low to 0. Then we will apply that function to each item in sentiment intensity, and then we will drop any rows where sentiment intensity is none, where sentiment intensity was something other than high, medium, or low. Finally, we will convert the sentiment intensity column to a tensor. In this video, you've been guided through the process of preparing raw text data for fine-tuning a machine learning model. You learned how to clean the text by removing unnecessary characters, tokenize it using the BERT tokenizer, handle missing values, and structure the cleaned and tokenized data into a format ready for fine-tuning. Now that you've learned how to prepare your dataset, try applying these techniques to your own data. With the right dataset, you're set for a successful fine-tuning process. Picture this. You are working with a pre-trained model, but your hardware is limiting how far you can push its performance. What do you do? In this video, we'll walk through the exact fine-tuning techniques, traditional, low-rank adaptation, or LoRa, and quantized low-rank adaptation, or QLoRa, that can help you adapt your approach and achieve great results no matter your computational restraints. We'll go step by step through the process and analyze how each method performs. You'll see how each method works, the results for each, and how to analyze the trade-offs between them. By the end of this video, you'll be able to apply traditional fine-tuning, LoRa, and QLoRa to pre-trained models. You'll be able to compare the computational efficiency and model performance of each fine-tuning technique, and understand how to choose the best fine-tuning technique based on hardware and task requirements. Step 1 is to create a new Jupyter notebook. I will call it Fine-tuning Comparison. Once the notebook has been created, I will select the appropriate Python kernel, and now we can start running our Python code. The first step in any fine-tuning process is preparing the dataset. For this activity, we used a task-specific dataset and split it into training, validation, and test sets. Do this by splitting the dataset into 3 parts. Here, we import the necessary libraries. We load a sample dataset from scikit-learn, and then we split the data into training, validation, and test sets. As usual, once I've finished pasting this code, I press Shift-Enter to run it and proceed to the next cell. Here, we split the dataset into 3 parts: training, validation, and test. This ensures that the model is trained and validated effectively, and the test set helps evaluate performance. Now, we'll tokenize the data. Here, we use the BERT tokenizer to tokenize our data. We define a tokenization function, and then we convert to datasets and tokenize. Here, we apply tokenization and keep only the necessary columns in our dataset: input IDs, attention mask, and label. Then, we will create a small sample for demonstration, only 2.5% of our training data. Then, we will print that training sample. Here, you can see the dataset format that we will use for fine-tuning. We see a label, input IDs, containing the tokens, and the attention mask. Step 2 is traditional fine-tuning. In this part of the activity, we apply traditional fine-tuning to the pre-trained model. This means we update all of the model's parameters during the training process. First, we import from transformers, these packages. Then we initialize the BERT model and load our training arguments. Here, we have changed the number of train epochs to 1 to complete this task more quickly, although results may be affected. We will only train for 1 epoch here, since we are limited to a compute instance without a GPU. Had we access to a GPU, we would train on the data for longer. Then we will initialize the data collator and initialize the trainer. Finally, we will train the model. We will call trainer.train, and once the model has finished training, we will print training completed and print the training loss that occurred. Then we will save the model for later use. Here, we loaded a BERT model and applied traditional fine-tuning where all the model's parameters are updated during training. Observe the compute instance, CPU, and memory usage, and the time until the model has finished training. We can see that it took us a total of 9 minutes to train this model on only one epoch, and in the meantime we were using nearly 100% CPU usage and 82% of our RAM. Quite a bit. Let's see if we can speed that up a bit and reduce the memory usage. Since we've already used so much memory here, what I'm going to do is close this notebook and create a new one. I will call this one LoRa, because now we will use low-rank adaptation, which allows us to update only low-rank matrices added to specific layers, while freezing the rest of the model's parameters. Let's repeat the steps we already took previously by importing the necessary libraries. Making sure, of course, that you have the correct kernel selected. And we will also tokenize our data again. Now that our tokenization has completed, let's start training the LoRa model. I'll add one more line here since it seems that we don't have the PEFT package installed. Okay. First, we initialize the BERT model, and then we define a LoRa configuration. We define the rank of the update matrices, the alpha scaling factor, then we apply LoRa to the attention layers, we define the dropout probability, and we decide not to train in bias terms. Then we create a LoRa model using PEFT. Then we set the number of training epochs again to 1 to save time, although this will affect the accuracy of our model later. We will initialize a data collator, initialize a trainer, and then we will train the model. It looks like I forgot one more import here, so I'm going to put it up here. And since we've already installed PEFT, I'll remove this line and press Shift-Enter to run again. By applying LoRa to the attention layers, we only fine-tuned the low-rank matrices, making the process more memory efficient. This reduced memory usage, but still provided competitive model performance. We can see that our code executed in 6 minutes and 12 seconds, with a training loss of 1.16. We also see that our memory usage is substantially less than it was with the traditional fine-tuned model. Finally, we will fine-tune with QLoRa. QLoRa, quantized low-rank adaptation, combines quantization and low-rank adaptations for even greater memory efficiency. Let's create a new Jupyter notebook. And I will call it QLoRa. I will make sure I have the appropriate kernel selected. and I will run the code to import the necessary libraries and load and tokenize the dataset as we did with the traditional fine-tuning and LoRa tasks. Now we will define and train our QLoRa model. Making sure, of course, to import all necessary libraries. Here, we took many of the same steps that we took when fine-tuning our model using the traditional method and when using LoRa. We initialize a BERT model. We define a LoRa configuration with explicit layer names and a LoRa config object. We apply LoRa, and we set the number of training epochs again to 1 to give us a better comparison between the training methods and to reduce the amount of time that we have to spend training on our CPU. Here, we disable GPU or FP16 options, meaning that the model is not saved in a floating point configuration, it is saved in an integer configuration. That is, the floating point numbers have been quantized to integers. We initialize the data call later, initialize the trainer, and train the model, saving it to QLoRa_model for later comparison. Here, we see that training this time only took 4 minutes and 30 seconds, consumed about the same amount of memory as our previous LoRa model, and our training loss was 1.12. QLoRa quantizes the model's parameters, e.g. from 32-bit floats to 8-bit integers, and applies LoRa to certain layers. This drastically reduces memory usage and inference, making it ideal for resource-constrained environments. Now that we've completed fine-tuning using all 3 techniques, let's compare the results in terms of training time, memory usage, and model performance. First of all, traditional fine-tuning. All parameters are updated, high memory usage, and moderate training time. LoRa has lower memory usage, faster training, and competitive performance. And QLoRa has minimal memory usage, the fastest training, but still competitive performance. To compare the performance overall, traditional fine-tuning took the longest and used the most memory. LoRa reduced memory usage and training time without sacrificing performance. QLoRa was the most efficient in terms of memory and time, with slightly lower but acceptable performance. In this video, we compared 3 fine-tuning techniques: traditional fine-tuning, low-rank adaptation, and quantized low-rank adaptation. You learned how to apply each method step by step, starting with dataset preparation, followed by fine-tuning the pre-trained model using traditional methods, LoRa and QLoRa. We then analyzed the performance, memory usage, and training time of each technique to demonstrate how they stack up for different tasks and hardware constraints. Traditional fine-tuning requires the most memory and time, but offers strong performance, while LoRa and QLoRa reduce memory usage and training time without significantly sacrificing accuracy. Now that you've seen the comparison, try applying these techniques to your own dataset. Depending on your hardware and task, LoRa or QLoRa might be the best choice for efficient fine-tuning. Experiment with LoRa or QLoRa to optimize for memory efficiency and the training time based on your hardware and task requirements.
In real-world scenarios like fraud detection or medical diagnoses, a high-accuracy model isn't always enough. In this video, we'll show you how precision, recall, and other metrics can make or break your model's success in mission-critical tasks. By the end of this video, you'll be able to explain the role of different evaluation metrics in assessing model performance, how to choose the right metric depending on your task, why accuracy isn't always the best metric, and how other metrics like precision, recall, and F1 score come into play. So, you've fine-tuned your model and you want to know how well it performs. You run it through some data, and your model spits out some results. But just looking at accuracy alone doesn't always tell the full story, especially when you're dealing with real-world problems where the cost of false positives or false negatives could be significant. First, let's talk about why accuracy isn't always enough. Accuracy seems like a good starting point. After all, who doesn't want a model that gets most predictions right? But here's the thing, accuracy can be misleading. Let's take a simple example. Say you're building a fraud detection model. If only 1% of transactions are fraudulent, a model that predicts not fraud for every transaction will have 99% accuracy. Well, that sounds good, right? Well, not if it's missing every actual case of fraud. Next, let's talk about precision and recall. If your fraud detection model catches all fraudulent transactions, but also flags a bunch of legitimate ones, you might have high recall, but low precision. In a scenario where investigating false positives is expensive, you'd care more about that precision. Here are some key points to keep in mind. Precision helps when false positives are costly, like in fraud detection. Recall is critical when missing positive cases, or false negatives, is dangerous, like in medical diagnoses. Now, what if both false positives and false negatives matter? That's where the F1 score comes in. It gives you a balanced measure, considering both precision and recall. It's super useful when you want to ensure your model isn't skewing too far in either direction. However, you should also be aware there are a number of emergent metrics that you can use, metrics which require you to know things like precision, recall, F1, or accuracy. Some of these, like ROC-AUC, help you understand how well your model distinguishes between classes, especially in imbalanced data sets. And let's not forget the trusty confusion matrix. It's a great tool to visualize where your model is making mistakes, whether it's false positives or false negatives. So, how do you choose the right metric? It depends on your task. If you're building a model for something like cancer detection, you might prioritize recall to ensure you catch as many cases as possible. If you're working on fraud detection, precision might be more important because you don't want to flag legitimate transactions unnecessarily. Choosing the right metric is crucial to building models that actually serve your end goals and minimize errors that could be costly in the real world. In this video, we explore the importance of evaluation metrics in assessing model performance, going beyond accuracy to examine precision, recall, F1 score, ROC-AUC, and the confusion matrix. You learn how accuracy alone can be misleading in certain contexts, such as fraud detection, and how metrics like precision and recall help capture the nuance of false positives or false negatives. We also discussed the F1 score's role in balancing precision and recall, and when to use more advanced metrics like ROC-AUC. Choosing the right metric depends on your specific task and what errors are most costly in your application. Now, try applying some of these metrics to your own model. See where it excels and where it might need just a little more fine-tuning. How do you adapt a general-purpose AI model to master a specific task like sentiment analysis or fraud detection? What if you could unlock the full potential of pre-trained models with just a few adjustments? In this video, we'll explore how fine-tuning can do exactly that. By the end of this video, you'll be able to explain what fine-tuning is and why it's essential. Describe the different techniques used for fine-tuning. Describe when and how to apply fine-tuning for optimal performance. Fine-tuning is all about taking a general-purpose, pre-trained model and adapting it to your specific task, whether that's text classification, sentiment analysis, or even fraud detection. By fine-tuning, you can use the model's pre-existing knowledge and save on training time and resources. At its core, fine-tuning involves updating the model's parameters to your task-specific dataset. This process enables the model to specialize in your task, whether it's text generation, image classification, or translation. But it doesn't stop there. There are various fine-tuning techniques, each suited for different use cases. We've covered 3 main approaches to fine-tuning: traditional fine-tuning, LoRa, or low-rank adaptation, and QLoRa, quantized low-rank adaptation. Each of these techniques offers different benefits depending on your hardware and resource constraints. Traditional fine-tuning updates all the model's parameters. It works well when you have sufficient resources and data. LoRa focuses on updating low-rank matrices in certain layers of the model, which is more resource efficient while still achieving good performance. QLoRa goes even further by combining quantization with low-rank adaptation, making it ideal for large models that need to be fine-tuned on resource-constrained hardware. Now that you know the benefits, here are some guidelines for selecting a fine-tuning approach. Choose a pre-trained model that aligns with your task. For instance, BERT is great for text classification. Then choose the right technique. Use traditional fine-tuning if you have the resources. Opt for LoRa or QLoRa if you're constrained by money or compute power. Next, evaluate your model. Always evaluate the fine-tuned model using relevant metrics like accuracy, precision, recall, and F1 score. In this video, we wrapped up everything you need to know about fine-tuning pre-trained models like BERT for your specific tasks. You learned how fine-tuning leverages pre-existing knowledge in models, saving time and resources. And we reviewed 3 main fine-tuning techniques: traditional fine-tuning, LoRa, and QLoRa. Each technique offers unique benefits depending on the resources available and the task at hand, from updating all model parameters with traditional fine-tuning to using LoRa or QLoRa for more efficient fine-tuning on limited hardware. We also emphasize the importance of selecting the right pre-trained model and evaluating your model using metrics like accuracy, precision, and recall. Now it's your turn. Take what you've learned and apply it to your own models. Whether you're using traditional fine-tuning, LoRa, or QLoRa, fine-tuning gives you the power to make your models work for you.
How do you turn a pre-trained language model into a specialized tool that's perfectly tailored to your project? Is it possible to get the precision you need without starting from scratch? In this video, we'll explore how fine-tuning can help you achieve that. By the end of this video, you'll know how to set up and fine-tune a pre-trained large language model, or LLM, prepare a dataset and optimize the fine-tuning process, and evaluate the performance of the fine-tuned model and understand the results. First things first, let's set up the environment and get everything ready to fine-tune the model. I'll start by creating a new Jupyter notebook. I will name it Fine-tune. And make sure I have the appropriate version of the Python kernel selected. We will be using the Hugging Face Transformers library for our task. First, we will import the Transformers library and any other libraries we need. And then we will load this pre-trained model, BERT, and the tokenizer from the Hugging Face Model Hub. We are looking at a BERT model for a text classification task. This model will act as the base that we fine-tune using our specific dataset. Next, we need to load and pre-process the dataset. This is a key step because the model needs to learn from task-specific data. While this is running, I will explain what the code does. First, we load a dataset, for example, the IMDb dataset, from the datasets library, which hooks into Hugging Face's dataset repository. Then we will use train test split to split the dataset into training and test sets. Then we will tokenize the dataset using the tokenizer that we defined earlier. And then we will create train data and test data for use fine-tuning our model. By tokenizing the text and splitting the dataset, we ensure that the model can efficiently process the input and learn the patterns necessary to perform the task. This step is essential for effective fine-tuning. Now for the most critical part, fine-tuning the model on our specific dataset. We'll configure the training parameters and run the fine-tuning process. I press Shift-Enter to automatically run the code and proceed to the next cell. While the trainer is training, let's talk about what the code does. First, we're going to take a subset of our dataset to speed up the training process significantly. You should comment out this code if you're training on a GPU. However, we are using only a CPU for training in this case, which means that our training process will be significantly slower. For the sake of time, we are only going to train on a smaller part of our dataset. We're also going to only train on half of an epoch to speed up the training process even more. We will define the trainer object for fine-tuning, and then we will fine-tune the model. Here, we've trained the model with a learning rate of 2e to the negative 5 and trained it for 0.5 epochs. These parameters are just a starting point, and you can adjust them based on your dataset and requirements. Once the fine-tuning is complete, it's time to evaluate how well the model has been adapted to the task. We will evaluate the model on the test set and then print and interpret the evaluation metrics. After evaluating the model, you'll be able to see how well it performs on the test set. This helps determine whether the fine-tuning process was successful and whether further optimization is needed. This is the evaluation loss, commonly cross-entropy loss in classification tasks such as this. It quantifies how well the model's predictions match the true labels on the evaluation or the test dataset. Lower loss values indicate better performance, with a perfect model having a loss close to 0. However, a loss of 0.055 suggests that there is room for improvement, but it depends on your specific task and data. If you want to further improve your model's performance, you can experiment with hyperparameters like learning rate, batch size, or the number of epochs. Let's see how you can adjust these values. Here, you can modify the hyperparameters by increasing the number of training epochs and changing the learning rate and having a larger batch size. Then you can retrain with new hyperparameters and evaluate the model and print the accuracy score. However, I'm not going to run this code here because running with this many epochs and with this batch size and learning rate on this particular compute instance would take a very long time and may actually crash the instance given the amount of memory I have. but by experimenting with different hyperparameters, you can achieve even better performance. Try tuning these settings to see if your model improves on key metrics like accuracy or recall. In this video, you reviewed the process of fine-tuning a pre-trained large language model like BERT. You learned how to set up the environment, load and pre-process a task-specific dataset, and fine-tune the model using Hugging Face's Trainer API. You defined training parameters like learning rate and batch size, and evaluated the model using metrics such as accuracy and recall. Additionally, you explored how adjusting hyperparameters can further optimize the model's performance. Now it's your turn to fine-tune an LLM on your own dataset. Compare your results, experiment with hyperparameters, and optimize your model for even better performance.
How does a self-driving car know when to stop, go, or turn? How does a virtual assistant know exactly how to respond to your request? In this video, we'll uncover the secrets behind AI agents and how they're shaping the future of autonomous decision-making. By the end of this video, you'll be able to explain what AI agents are and how they function, the different types of AI agents and their applications, and why AI agents are essential in solving real-world problems. An AI agent is essentially a program or system that can make decisions, take actions, and interact with its environment autonomously to achieve specific goals. Think of it like a virtual assistant or a self-driving car. These agents are designed to perceive their environment, process information, and act accordingly, all without human intervention. They do this through a cycle of sensing, thinking, and acting. This is called the perceive, think, act cycle. First, perceive. The agent gathers information from its environment using sensors or input data. For example, a self-driving car uses cameras and LiDAR to perceive road conditions. Next, think. The agent processes that information, deciding on the best course of action. This could involve complex decision-making algorithms, learning models, or even optimization techniques. Finally, act. The agent takes its requested action. Whether it's a chatbot responding to a user or a robot moving an arm, this step is where the agent applies its decisions to affect the environment surrounding it. AI agents come in many shapes and sizes, depending on their complexity and functionality. Let's break them down into a few more common types. First up, simple reflex agents. These agents make decisions based purely on current input. For example, a thermostat adjusting temperature based on a current reading. Next, the model-based agent. These agents maintain some internal representation of the environment. For example, a vacuum robot that creates a map of the room and decides on its cleaning path. Next, goal-based agents. These agents take future goals into account when making decisions. They prioritize actions that move them closer to achieving those goals. For example, think about how a delivery drone plans a route to deliver a package. Instead of just reacting to immediate obstacles, it considers the final delivery location and adjusts its path to ensure the quickest and most efficient delivery. Next are utility-based agents. These agents optimize actions based on a utility function, meaning they don't just reach a goal, but find the best way to do so, like a self-driving car calculating the fastest, safest route. AI agents are revolutionizing industries by automating tasks, improving decision-making, and creating more responsive, intelligent systems. Here are 3 real-world examples of AI agents in action. In healthcare, AI agents assist doctors in diagnosing diseases and personalizing treatment plans. In finance, agents monitor stock markets and make split-second trading decisions. In customer service, virtual agents handle inquiries, reducing the need for human intervention in call centers. In this video, we explored the world of AI agents and how they autonomously make decisions, interact with their environment, and achieve specific goals without human intervention. You learned about the perceive, think, act cycle, which governs how AI agents function as well as the different types of agents, from simple reflex agents to utility-based agents. We also covered real-world applications of AI agents in healthcare, finance, customer service, and autonomous vehicles, showcasing their transformative impact across industries. Now that you understand the power of AI agents, start exploring how you can apply these concepts in your own projects, whether it's developing a chatbot, creating an autonomous system, or improving decision-making processes in your field. Picture a fleet of delivery drones, each working together to make deliveries faster. Now imagine stock market bots competing for the best trades. These are two types of multi-agent systems, and in this video, we'll explore how cooperation and competition play out in real-world scenarios. By the end of this video, you'll be able to describe the main types of multi-agent systems, how cooperative and competitive systems differ, and how hybrid systems combine the best of both worlds. Multi-agent systems come in different shapes and sizes, and how the agents interact is the key difference. Let's break it down into three main categories: cooperative, competitive, and hybrid. First up, cooperative systems. In a cooperative multi-agent system, all agents share the same goal. They work together, share information, and coordinate their actions to achieve the best outcome for the group. Think about a fleet of delivery drones. Their common goal is to deliver all packages as efficiently as possible. They share information about traffic, weather conditions, and delivery routes to optimize that performance. On the flip side, let's look at competitive systems. A competitive multi-agent system is acting in its own self-interest. These agents compete for resources or rewards, and they don't necessarily share information with each other. In the stock market, for example, trading bots represent different companies or investors. They compete to buy and sell stocks at the best prices, aiming to maximize profit without helping others. Next up, the hybrid system. Hybrid multi-agent systems are a combination of both cooperative and competitive elements. In these systems, some agents might cooperate within subgroups, but still compete against other groups or other agents. Imagine a multiplayer game where team members cooperate to achieve objectives, but the teams themselves compete against one another to win the match. The way agents communicate and coordinate their actions also varies depending on the type of multi-agent system. In a cooperative system, communication is often direct and open. Agents share data, synchronize action, and sometimes even split tasks to optimize performance. These systems are all about teamwork. For example, a search and rescue operation, which includes a swarm of drones. Each drone takes a specific area to search, and they report their findings to a central base to avoid information duplication. In competitive systems, communication is far more strategic, and agents may withhold or manipulate information. Coordination isn't as direct since agents are often working against one another. Going back to our stock market example, trading bots may not share strategies or market insights. Instead, they try to outsmart one another by predicting market movements and responding quickly to changes. Emergent behavior is another key difference in multi-agent systems. This occurs when the actions of individual agents lead to complex, often unexpected outcomes on a larger scale. In a cooperative system, emergent behavior can result in highly efficient solutions. For example, a group of robots might find the optimal cleaning pattern for an entire warehouse, even though each robot is only programmed to clean specific sections. In competitive systems, emergent behavior might lead to market fluctuations or the rise and fall of certain strategies over time. Even though each agent is acting in its own interest, their interactions can have broader, system-wide effects. In this video, we explored the different types of multi-agent systems: cooperative, competitive, and hybrid. You learned that in cooperative systems, agents work together toward a shared goal, while in competitive systems, each agent acts in its own self-interest. Hybrid systems combine elements of both, with agents cooperating in groups while competing against other groups. We also discussed how communication and coordination vary between these systems and how emergent behavior can lead to unexpected results depending on whether the agents are working together or working against one another. Now that you understand the different types of multi-agent systems, think about how these interactions apply to your projects and start designing a system that aligns with your goals, whether it's cooperative, competitive, or hybrid.
Managing resources efficiently is one of the biggest challenges in industries like logistics and supply chain management. What if autonomous agents could solve these problems for you? In this video, you'll see a multi-agent system in action, showing how it tackles resource allocation with precision. By the end of this video, you'll be able to explain how a multi-agent system handles resource allocation and management, describe how agents collaborate to optimize resource usage while minimizing conflicts, and describe the implementation of communication, coordination, and decision-making among agents in a real-world simulation. In this case, we're simulating a multi-agent system for warehouse management. Imagine a scenario where multiple autonomous robots, agents, are tasked with handling different inventory items across various sections of a large warehouse. Their goal is to pick and move items efficiently without bumping into each other or duplicating tasks. Each robot acts as an independent agent with its own goals and tasks, but they must communicate and coordinate to avoid conflicts and ensure that all sections are covered without inefficiency. Let's set up the environment first. I'll start by creating a new Jupyter notebook, and I will call it Warehouse Simulation. I will select the appropriate Python kernel, though it shouldn't matter for this particular activity, and press Shift-Enter to run this code. Here, we define a class called Warehouse with a number of sections within the warehouse. You can store an item in the warehouse, or you can retrieve an item from a section of the warehouse. We will also have 10 autonomous robots, each assigned to handle tasks like retrieving or restocking inventory. Let's define what a task is in this simulation. We can see that tasks have a type, have a location, and have an item. And we can also define what a robot is in this situation. Here we can see that a robot exists within a warehouse, that it has a position, a task, and can measure the distance from the robot's current position to a given location. It can also reassign a task or mark a task as complete if it has retrieved or stored, restocked an item successfully. Now, let's define our warehouse environment by initializing a warehouse and 10 autonomous robots, each in a different section. Each robot is assigned an initial position in the warehouse. They are now responsible for completing tasks within their sections, such as retrieving specific items and moving them to different areas for shipping. Here, we define a function to allocate a task by finding the nearest robot for a specific task. We define an example task here, which is to retrieve an item called widget A from location 3, 2. That is from section 3 within the warehouse. And then we allocate the task to the robots. Here, the task is allocated to the robot that is closest to the item's location. This ensures that tasks are completed efficiently without wasting time or energy. The other robots continue with their tasks or stand by for the next task. In a busy warehouse, robots might cross paths or attempt to pick up the same item. This is where communication and coordination come in. If two robots are headed for the same location, they'll need to communicate and adjust their routes to avoid collisions or task duplication. Here, we define a function called resolve conflict that resolves a conflict when two robots are headed for the same item. If both robots have been assigned to the same task, we then prioritize the robot that is closer to the task location. Here, we have two robots assigned to the same task and use the resolve conflict function to choose one of them. By resolving conflicts in real time, the system avoids delays and potential collisions. In this case, if two robots are about to retrieve the same item, the system prioritizes the robot closest to the task while reassigning the other robot. As the robots continue to work, an interesting phenomenon occurs: emergent behavior. Although each robot is only programmed with local tasks, their collective actions result in an optimized workflow for the entire warehouse. For example, if a section becomes overloaded with items to retrieve, nearby robots can adapt by picking up additional tasks, effectively balancing the workload across the entire system. This emergent behavior leads to higher efficiency without requiring any centralized control. Some multi-agent systems also involve learning and adaptation. Let's say our warehouse robots are using reinforcement learning to improve their task performance over time. By learning from previous tasks, they can optimize their paths, avoid conflicts, and even predict which sections will need more attention. Here, we define a function to reward our robot for completing tasks without conflict. If the task was completed successfully, we give a reward to the robot for a successful task completion. Else we penalize the robot for failing to complete the task. For example, for each robot in our group, we tell the robot to complete its task. If the robot was able to complete its task, then we give it a reward. If the robot failed to complete a task, then we give it a penalty. As the robots learn from their experiences, they become more efficient at navigating the warehouse and coordinating with other robots. Over time, this learning improves overall system performance. In this demonstration, you've seen how a multi-agent system can be applied to solve a resource allocation problem in a warehouse setting. You've learned how multiple autonomous agents, robots in this case, handle tasks like retrieving and restocking items while collaborating to avoid conflicts and maximize efficiency. You saw how task allocation, communication, and conflict resolution enable these robots to work together, resulting in emergent behaviors that optimize workflow. You also touched on the concept of learning and adaptation, where agents improve over time using reinforcement learning. Now that you've seen how multi-agent systems can solve complex tasks efficiently, consider how you can apply similar strategies to improve operations in industries like logistics, healthcare, or manufacturing. Start exploring ways to implement these systems in your projects.
Think about the number of devices you rely on each day. Your phone, car, or even your watch. What happens when things go wrong? Instead of waiting for tech support, how about having an AI system troubleshoot the problem in real time? Let's dive in and discover how AI is making this a reality. By the end of this video, you'll be able to describe how AI troubleshooting is applied across different industries, explore real-world examples where AI agents have improved problem-solving efficiency, and learn how AI systems are reducing the burden on human technicians by automating the troubleshooting process. Let's start with something we've all likely experienced: troubleshooting our smartphones. Companies like Apple and Google use AI-powered virtual assistants like Siri or Google Assistant, respectively, to help users fix common problems with their devices. These assistants can diagnose common issues like battery drain, app crashes, or connectivity problems. If your phone isn't charging correctly, for example, the assistant can walk you through checking your charger and software settings. In many cases, they can even reset system settings automatically. This reduces the number of customer service calls and empowers users to solve problems on their own, improving user satisfaction while easing the load on human technicians. Now, let's talk about a more technical application: AI troubleshooting in IT infrastructure. Microsoft's Azure platform uses AI-driven monitoring and troubleshooting tools to detect and resolve issues in cloud environments. For example, if there's a server downtime or a networking issue, the AI system can identify the root cause and attempt to fix it, whether it's by reallocating resources, restarting services, or notifying appropriate personnel. By automating these fixes, the system can prevent extended downtime, improve operational efficiency, and minimize human intervention. This is especially critical for large enterprises, where even a few moments of downtime can result in significant financial loss. AI troubleshooting isn't just limited to software, however. It's making its way into physical systems too. Modern vehicles, especially electric and autonomous cars, rely on AI systems to monitor and troubleshoot issues in real time. Take Tesla's vehicles, for instance. These cars use AI to diagnose problems with everything from the battery to the sensors. If there's an issue with the autopilot system, the car can alert the driver, and in many cases, resolve minor software glitches on its own by rebooting or recalibrating systems, all while driving. This kind of AI troubleshooting enhances safety, reduces maintenance downtime, and allows drivers to keep their vehicles running smoothly without needing to visit a mechanic for every single minor issue. Let's take a look at how AI troubleshooting is transforming the telecommunications industry. Telecom companies like AT&T and Verizon use AI to manage their networks and handle customer complaints about connectivity issues. When a customer reports something like slow internet speeds, for example, the AI system can automatically check the user's network settings, scan for outages, and even perform remote resets. In some cases, the agent may fix the issue before the user even notices by adjusting bandwidth or rerouting a connection. With AI handling common network issues, telecom companies have reduced the number of service calls and improved response times, allowing human technicians to focus on more complex problems that require their attention. Finally, AI troubleshooting is making a huge impact in healthcare, especially with wearable devices like smartwatches. These devices, like the Apple Watch or Fitbit, not only track your fitness, but also detect hardware or software malfunctions. If a sensor in the watch is malfunctioning or the app isn't syncing with your phone, the AI system can troubleshoot and offer solutions like recalibrating sensors or restarting the software. In some cases, the watch can even notify the user that it's experiencing a hardware issue and it's time for servicing. AI-driven troubleshooting helps healthcare devices remain accurate and functional, ensuring users get the health data they need without interruption. And in a field as critical as healthcare, quick and accurate problem resolution, well, that's vital. In this video, we explored how AI-powered troubleshooting systems are transforming various industries by automating problem-solving processes. We looked at real-world examples from virtual assistants helping users fix phone issues to AI systems diagnosing server downtime in cloud infrastructures like Microsoft Azure. We also examined how AI helps resolve issues in vehicles like Tesla's cars, manage network problems for telecom companies, and ensures wearable health devices like smartwatches stay functional. AI troubleshooting is reducing the burden on human technicians while enhancing efficiency and user satisfaction across the board. Now that you've seen how AI troubleshooting is shaping industries, take a closer look at the devices and systems you use on a daily basis. Explore how AI is helping you troubleshoot issues behind the scenes, and think about how these advancements might benefit your future projects or workflows.
Ever get stuck troubleshooting tech problems for hours, only to end up doing an internet search for solutions? What if you had an AI-powered agent to handle those issues for you? In this video, we'll build a smart troubleshooting agent that can diagnose and solve common problems automatically. By the end of this video, you will be able to explain the core components of an intelligent troubleshooting agent, describe how to create a basic knowledge base and implement basic diagnostic logic, and describe how user interaction features are built and automate common fixes. We'll begin by setting up our programming environment. For this project, we are using Python along with libraries like NLTK or spaCy for natural language processing and a simple knowledge base to store our troubleshooting data. I'll begin by creating a new Jupyter notebook. I'll call it Troubleshooting Agent. And we will also create a file for our knowledge base. I will call it Troubleshooting Knowledge Base. .json.json. This setup provides us with the tools to process user input and interaction with the troubleshooting agent. Once we have our environment ready, we can begin building the agent's core functions. The first step in creating an intelligent troubleshooting agent is to build its knowledge base. This is where the agent will store known problems and their corresponding solutions. I've created an example knowledge base, which I will paste here. Here we create a simple JSON file that stores common issues and their solutions. It ensures that the knowledge base is structured in a way that allows easy retrieval of data. The code here shows a sample JSON, which includes common issues such as slow internet or a device not charging. The knowledge base is a simple database that the agent will query when diagnosing user-reported problems. The more comprehensive the knowledge base, the more helpful the agent will be in troubleshooting. Next, we'll implement the part of the agent that interacts with the user. Using natural language processing, or NLP, we can make the agent understand user queries and match them to problems in the knowledge base. Let's go back to our troubleshooting agent Jupyter Notebook. Let's make sure that Python 3.8 Azure ML is selected. I paste the code. The code will be available for you to copy and paste, and press Shift-Enter to run the code and proceed to the next cell. What this code does is import JSON, pipeline, and spaCy. It will load a pre-trained spaCy model for general natural language processing tasks, and it will initialize a question-answer NLP pipeline. Here, we load the troubleshooting knowledge base, and then we define a function to match user input to the most relevant knowledge base entry. For this, we gather the user input and change it to lowercase. And then for each issue and details in our knowledge base, we also convert them to lower input and use a natural language processing model to calculate the similarity between user input and symptom text. Here, the similarity is calculated by comparing the natural language processing result of the user input and the natural language processing result of the symptom text. If the similarity is greater than 0.75, 0.75 is just a placeholder here, we return the solution. Else, we say that no matching issue is found in the knowledge base. Then we gather user input, call the function to find the best match, and print out the solution. This code snippet allows the agent to understand natural language input from the user, search for relevant issues in the knowledge base, and provide a solution. It's a simple yet powerful way to make the agent more user-friendly. Let's test it by entering a query. Let's say that the printer is not working, and we are given a solution. Ensure that the printer is connected and check for paper jams. Troubleshooting agents often need to perform diagnostics. We can add a decision-making process that helps the agent ask follow-up questions and perform specific checks before offering a solution. Here we will implement a decision tree or rule-based system to guide the agent through a series of steps for problem diagnosis. We will create conditional logic for common problems like network issues or software errors. I'll add this code to our existing cell. Here, we define a function to troubleshoot internet-related issues with follow-up questions. Here, if the diagnose internet issue function is called, we print, "Have you tried restarting your router?" And then we ask for a response from the user. If the user hasn't restarted their router, we prompt the user to restart their router and check back if the issue persists. If the user already tried restarting, we suggest advanced troubleshooting. Try like resetting your network settings or contacting your provider. Let's restart the kernel and run all cells to run the troubleshooting agent with this new logic. I'll give an example query. I'll say that my internet is slow. And then I'm prompted to say, "Have you tried restarting your router?" I will say, "No." And then I am told to restart your router and check if the issue persists. By adding follow-up questions and diagnostic logic, we make the agent more interactive and capable of drilling down into specific issues. This makes troubleshooting more accurate. To speed up the troubleshooting process, we'll add automation for common fixes. This allows the agent to perform simple tasks, like resetting settings, without needing the user to do it manually. Here, we will implement functions that allow the agent to perform simple automated fixes, and we will set up simulated actions, like restarting services, so that the agent can perform them based on the diagnostic issue. Let's add this code to the decision tree. This code will run when the user says they have an internet connectivity problem, but have not already restarted their router. Automation of common fixes can make the troubleshooting agent more efficient, especially for frequently encountered issues like network problems or system restarts. Let's test this by restarting the kernel and saying that we have an internet problem, that our internet is slow. I will say that I have slow internet. but that I have tried restarting my router. And then the agent will automatically reset some basic network settings by running sudo systemctl restart systemd-networkd.service on my Azure machine learning compute instance. This will reset the network adapter on my compute instance and may resolve some common network connectivity problems. In this video, you walked through the process of designing an intelligent troubleshooting agent. You learned how to set up a Python environment, build a knowledge base, implement natural language processing for user interaction, add diagnostic logic, and even automate common fixes for issues like network problems. This step-by-step guide provided the tools and methods needed to create a troubleshooting agent capable of diagnosing and resolving common technical issues efficiently. Now that you've learned how to design a troubleshooting agent, start building one for a specific system or service you use. Customize the knowledge base, enhance the diagnostic logic, and automate fixes to create an efficient, user-friendly troubleshooting experience.
Have you ever wondered how AI can understand and process human language? Think of natural language processing, or NLP, as the bridge that connects human language to the world of machines. Just like a translator helps people from different countries communicate, NLP enables machines to understand our words, emotions, and in many cases, even our intentions. In this video, we'll break down the key techniques that make this possible. By the end of the video, you'll be able to explain the core NLP techniques used in AI. Discuss how these techniques are applied in real-world applications. And learn the impact of NLP on everything from chatbots to translation tools. Let's start with the foundation, tokenization. This technique breaks down a string of text into smaller units called tokens, which could be individual words, subverbs, or even glyphs. Tokenization helps AI systems process language piece by piece. Imagine, for example, you input the phrase, "the quick brown fox." Tokenization would split that into the, quick, brown, and fox. Each word becomes a token the AI can then analyze. Tokenization is the first step in many NLP tasks, from text classification to machine translation. Without it, AI systems wouldn't be able to make sense of longer, more complex sentences. Next up are lemmatization and stemming, two techniques used to reduce words to their root forms. This helps AI focus on the meaning of the word rather than its grammatical variations. Stemming chops off word endings. So, for example, running becomes run. Lemmatization, on the other hand, is more sophisticated and reduces running to run by understanding the word's context. It does this by identifying the word's part of speech and its intended meaning to ensure it converts the word accurately based on how it's used in a sentence. These techniques are especially useful in search engines and sentiment analysis, where it's important to treat variations of a word like runs, ran, and running as having essentially the same meaning. Named entity recognition, or NER, is all about identifying and classifying important information from a text. It pulls out entities like names of people, places, dates, or organizations. When you input a sentence like, "Serena Williams won the Wimbledon title in 2016, NER will tag Serena Williams as a person, Wimbledon as a location, and 2016 as a date. NER is used in document processing, customer support systems, and even in news aggregation tools to help identify key pieces of information automatically. Sentiment analysis helps AI determine the emotional tone of a piece of text. Is it positive, negative, or neutral. Sentiment analysis helps machines understand not just what's being said, but also how it's being said. Take this sentence, for example. I love this product. Sentiment analysis would classify that as a positive sentiment. On the other hand, I'm really disappointed with this service would be flagged as negative. This technique is widely deployed in social media monitoring, customer feedback analysis, and marketing, where understanding how people feel is crucial for decision making. One of the most well-known NLP applications is machine translation, which allows AI systems to translate text from one language to another. Systems like Google Translate break down sentences, analyze grammar and syntax, and map words from one language to another target language. Over time, these systems have become more accurate by using large data sets and deep learning models. Machine translation powers everything from translation tools to multilingual customer service chatbots, making cross-language communication easier than ever before. Text summarization helps AI systems condense large text into shorter, more digestible versions while preserving the most important information. There are two types of summarization: extractive, which pulls out key sentences, and abstractive, which generates a summary in its own words. Both approaches aim to shorten a text while retaining its meaning. This is useful in news aggregation, academic research, and anywhere people need to quickly understand the gist of a text within a larger body. In this video, we covered key natural language processing, or NLP, techniques that enable AI systems to understand and interact with human language. We explored tokenization, which breaks text into smaller units for analysis, and lemmatization and stemming, which reduce words to their root forms to focus on meaning. We also discussed named entity recognition, or NER, which identifies important entities like names and dates, while sentiment analysis helps AI detect emotional tone within text. Additionally, we discussed how machine translation allows AI to translate languages, and text summarization condenses long text into concise summaries. These techniques are essential for powering AI tools like chatbots, translation apps, and customer service systems, helping you understand how AI enhances communication and automation. Now that you've learned about key NLP techniques, take it a step further by analyzing how these methods are used in tools you interact with daily. Try identifying tokenization, sentiment analysis, or machine translation in action within apps like chatbots, translation tools, or virtual assistants. Start by picking a tool and then explore how NLP enhances its ultimate functionality.
Ever get frustrated waiting for tech support? Imagine if you could build a chatbot that answers user queries instantly any time of the day. In this video, you'll learn how to create your own interactive chatbot interface from scratch. You'll navigate the step-by-step process of building a simple yet effective chatbot interface that captures user input, handles responses, and simulates real-time conversations. By the end of this video, you'll create a basic chatbot interface using HTML, CSS, and JavaScript. Implement a system for capturing user input and providing chatbot responses, and add quick replies and error handling to improve the user experience. We'll start by setting up our environment. For this project, we'll be using basic web development tools like HTML, CSS, and JavaScript. You don't need any heavy frameworks, just a text editor and a browser to test your interface. Let's start by creating a new folder for this activity. Let's call it Agent Interface. Inside the folder, right-click and create a new file. We're going to create 3 files. One of them is called index.js. index.html. Another one is called styles.css. And the last one is called chatbot.js. Now, make sure that your compute instance is running. And we're going to open index.html in VS Code on your host machine. VS Code on your web browser won't work for this activity. VS Code desktop, click that, and allow ml.azure.com to open these links. VS Code opened on another monitor. I will drag it over here in a second so you can see it, but first I am sent a pop-up. It asks me if I'd like to install Azure Machine Learning Remote extension from Microsoft. I want to install it and open the URI. It will ask me to sign in using Microsoft, and I will click Allow. I will sign in. And wait for VS Code to initialize the connection to my compute instance. I'm given a security alert. And yes, I want to allow access. I also want to trust all the files in the, I want to trust all the authors of the files. Okay. Let's close the Welcome tab and view index.html. When prompted to enable autosave, click OK to enable it. Let's install the live preview extension. The extension we are searching for is called Live Preview from Microsoft. Now scroll down under your Azure ML Compute instance and confirm that the Live Preview extension is installed. Now let's go to the Explorer, right-click on index.html, and click Show Preview. Next, we'll create the basic layout of our chatbot interface using HTML and CSS. This layout will include a chat window to display the conversation and an input field for users to type their messages. I'm copying and pasting this HTML code. And when I paste it into the document, the preview on the right side of my VS Code window automatically updates. You can see that we now have a basic but unstyled interface where you can type a message and a button to send the message once you've finished typing. Now let's build our CSS. I am copying some CSS code and I will paste it into styles.css. This code will also be available for you to copy and paste. With our CSS code in place, you can see that the interface now looks much better. This code creates the basic structure for the chatbot interface. This means the messages div will display the conversation, while the user input section lets users type their queries and send them. Now, let's add some functionality to our chatbot. You can see if we try to send a message and click send, nothing happens. We'll use JavaScript to capture the user's message, display it in the chat window, and then simulate a chatbot response. Here, we will implement JavaScript to process user input and display both the user's message and the chatbot's response. Then, we will simulate a basic chatbot response based on predefined queries. Let's open chatbot.js. I will paste some JavaScript code. This code will also be available to you to copy and paste. This JavaScript captures the user's input and displays both their message and a chatbot response. We're using a basic response system that captures specific keywords. For example, if the user says hello, the response will be, "Hi, how can I help you today?" Let's test that. I will type hello in the message box and then click send. My message is displayed on screen, and then a moment later, the chatbot adds its own message to the screen. It says, "Hi, how can I help you today?" A good chatbot interface also handles errors gracefully. Let's add a mechanism for the chatbot to respond when it doesn't understand a message or when the input is unclear. For example, if I were to type a bunch of random key presses and then click send, the chatbot will respond with undefined. Let's modify our code now. If the responses field, if message.toLowercase in the responses field is undefined, we will instead return the string, "Sorry, I didn't understand that. Could you rephrase?" Let's try submitting the same random key presses as last time, and then click send. And now the chatbot says, "Sorry, I didn't understand that. Could you rephrase?" A much better response than simply undefined. By adding error handling, the chatbot can respond to unclear or unrecognized input in a helpful way, improving the overall user experience. You just built a simple chatbot interface using HTML, CSS, and JavaScript. You learned how to set up a basic environment, create the interface layout, implement user input handling, and simulate chatbot responses. We also covered how to add quick reply buttons for improved usability and error handling to create a more user-friendly experience. Now that you've built the basic chatbot interface, try enhancing it by experimenting with more complex responses, integrating real-time APIs, or adding back-end systems for dynamic conversations. Have you ever thought about how companies instantly know what customers think about their products? Imagine scanning through thousands of reviews and quickly spotting which features customers loved and which need improvement. In this video, we're diving into sentiment analysis, a powerful tool that helps businesses do just that. We'll walk you through a real-world example to show how it can transform raw customer feedback into actionable insights. By the end of this video, you'll be able to describe how sentiment analysis is applied in a practical use case, explain how sentiment analysis classifies text into positive or negative categories, and interpret the results of sentiment analysis for actionable insights. Let's imagine we're a company that sells smartphones, and we've just launched a new model. We want to analyze customer reviews from our website and social media to understand how well the product is being received. Sentiment analysis can help us quickly categorize thousands of reviews into positive or negative sentiment. Sentiment analysis works by processing text and assigning a polarity score to each sentence. Positive text receives a positive score, and negative text gets a negative score. Modern sentiment analysis can handle complex language patterns and even some nuances like sarcasm. Now, let's run a few sample reviews through our sentiment analysis model. I'll start by creating a new Jupyter notebook. I'll name it Smartphone Sentiment Analysis, if I can spell. We'll use a pre-trained model that's built for sentiment classification. The model will process each review and output the sentiment score. I will make sure to select the correct Python kernel, Python 3.8 Azure ML, and I will paste this code. You will also have access to this code to paste and run yourself. Now I will press Shift-Enter to run the code while I explain what it does. First, we import pipeline from Hugging Face's transformers library. Then we initialize a pre-trained sentiment analysis model from a pipeline. Here we define some sample customer reviews. One customer says the battery life on the phone is amazing. One says they hate the camera quality, and one says the design is just okay, but nothing special. Now we're going to run some sentiment analysis. For each review in our reviews, we'll define result is equal to sentiment analyzer. As a reminder, sentiment analyzer is our pipeline, sentiment analyzer of the review. Then we will print the review and the sentiment, what this looks like. After ignoring these error messages, mostly related to CUDA that we can ignore, we see review, the battery life on this phone is amazing, correctly identifies the sentiment as positive. Review, I hate the camera quality, correctly identified as negative. And review, the design is okay, sentiment is negative, and we also see the scores for each one. Here, the sentiment analysis model processes each review and classifies it as either positive or negative with a confidence score. Sometimes sentiment analysis models will give negative scores to negative sentiments. However, in this case, the model will give a negative label and a positive score. It's important to know which type of model you're using so you understand what kind of results are expected. Looking at the results, we can see that the sentiment analysis classified the first review as highly positive, the second as highly negative, and the third as less negative, 0.99 versus 1.00. In this case, we see that people love the battery life but are unhappy with the camera quality. Sentiment analysis can be applied to a wide range of industries, from tracking brand sentiment on social media to analyzing customer feedback after product launches. This tool allows companies to make data-driven decisions. In our case, if we notice a trend of negative feedback about the camera, we could work on improving that feature in future models. In this video, you saw how sentiment analysis can quickly categorize customer feedback into positive or negative sentiment, helping companies get valuable insights at scale. Whether you're a marketer, product manager, or customer service representative, sentiment analysis is a powerful tool for understanding how people feel about your product or brand. Now that you've seen how sentiment analysis works, try applying it to your own data. Analyze customer feedback, track social media sentiment, or even explore new ways to gain insights from text. Sentiment analysis is everywhere, from product reviews to social media monitoring. But how do we build it? In this video, we'll walk you through how to implement a basic sentiment analysis model step by step and show you how to analyze the sentiment of real-world text data. By the end of this video, you'll be able to describe how to implement a sentiment analysis model using a pre-trained pipeline, input both predefined and custom text for sentiment classification, and interpret the results and evaluate sentiment analysis in practical applications. Let's start by setting up our Python environment. I will begin by creating a new Jupyter notebook. I will call it Sentiment Analysis. Then I will make sure that I have the Python 3.8 Azure ML kernel selected. We'll be using the transformers library from Hugging Face to implement sentiment analysis with a pre-trained model. First, let's make sure that we have the required libraries installed. I will press Shift-Enter to automatically run the cell and proceed to the next one. We see that the requirement is automatically satisfied, so we know that that particular library is already installed. If you get any error messages saying that a module is not found, then you can use !pip install module name to install the module. However, Before you do that, please be mindful and make sure that you've selected the Python 3.8 kernel. It's likely that the module is already installed. The libraries we will use give us access to powerful pre-trained models, including BERT-based models, which are highly effective for tasks like sentiment analysis. Once the environment is set up, we can load a pre-trained sentiment analysis model using the Hugging Face pipeline function. This simplifies the entire process, allowing us to focus on analyzing text. Here, we load the sentiment analysis model using the pipeline function from the Transformers library. I've copied and pasted this code into my Jupyter notebook. This same code will be made available for you to copy and paste. And again, I press Shift-Enter to run the code. Here, we create a pipeline named Sentiment Analyzer using the model Distilbert base uncased fine-tuned SST-2 English. Once that is completed, we print a message to say that the sentiment analysis model was loaded successfully. These error messages can be safely ignored because most of them have to do with a lack of CUDA functionality. We are using a compute instance without a GPU, so we will not have CUDA available, and these messages can be safely ignored. This code loads a pre-trained sentiment analysis model that's already trained on a large corpus of data. It's ready to process text and classify it as positive or negative. Let's start by running some predefined text samples through the model to see how it classifies them. This will give us a quick idea of how the sentiment analysis system works. Here, we define some sample texts for sentiment analysis. For example, I love this product. It's amazing. The service was terrible and I'm very disappointed. And it's okay. Not great, but not bad either. Now, for each text in these texts, the result is set equal to Sentiment Analyzer, the sentiment analysis pipeline we defined earlier, of that text. Now we print the text, the sentiment, and the confidence the Sentiment Analyzer has in its sentiment score. Here, we see that the analyzer correctly identifies this review as positive. It says, I love this product, it's amazing. It correctly identifies this review as negative. The service was terrible and I'm very disappointed. And it identifies this review, it's okay, not great, but not bad either, as positive. We can see that this particular sentiment analyzer, this particular model that we've selected, will try to fit everything into either a positive or negative category. You may want to choose a different model if you also want to classify sentiment as neutral, as is the case with this review. The sentiment analysis model classifies each text as either positive or negative. It also provides a confidence score to show how certain the model is about its classification. Now that we've seen how the model handles predefined text, let's allow users to input their own sentences for sentiment analysis. This makes the model interactive and flexible. Here, we prompt the user to enter a sentence for sentiment analysis. Once that is done, we analyze the sentiment. We print the sentiment score and confidence. Let's say, this course is amazing. I learned a lot, and submit that. The sentiment analyzer correctly identifies the sentiment as positive with a confidence score of 1.0. With this feature, users can input their own sentences and immediately see the sentiment classification, making the tool more engaging and practical. Once we've tested a few examples, it's important to reflect on how well the model performed. Did it correctly classify the sentiment of each sentence? Were there any cases where the results were unexpected? You should review the outputs and discuss how sentiment analysis can handle different types of language, such as strong emotions or mixed sentiments. For example, if the model classified a sentence like, "It's okay, but not great," as neutral, that's expected because the sentiment is mixed. But if it's misclassified something like, "I'm not happy with this service," as positive, we might need to explore ways to improve the model's accuracy with more training data. In this video, you saw how to implement a sentiment analysis model using a pre-trained pipeline. We tested both predefined and custom text inputs, and we saw how the model classified text as either positive, negative, or neutral. Sentiment analysis is an incredibly useful tool for understanding how people feel about products, services, or even events. Now it's your turn. Try applying this sentiment analysis model to real-world data, whether it's social media posts, customer feedback, or product reviews. You'll be amazed at the insights you can uncover.
Have you ever wondered why some NLP systems struggle to get even simple tasks right? It's not just about using the right components. It's about how you connect and coordinate them effectively to work together. In this video, we'll walk you through best practices to combine key NLP techniques for smooth and accurate results. By the end of this video, you'll be able to explain how to effectively combine NLP components such as tokenization, POS or part of speech tagging, and sentiment analysis. You'll be able to explain the importance of data pre-processing and compatibility between components, as well as describe common pitfalls to avoid and best practices to follow for successful integration. The first best practice is making sure your data is pre-processed properly. This means removing unnecessary noise like punctuation, special characters, or even emojis, depending on your use case. If your data isn't clean, even the best models won't give you accurate results. So here's a tip to make sure you can follow this best practice. Standardize your text by converting it to lowercase, removing irrelevant characters, and handling stop words. Stop words such as the, is, in, and, of, as well as to, do not carry significant meaning on their own and are often removed from a corpus to focus on the more important content-rich words within a text. Once standardized, the next process is tokenization. Tokenization is one of the most crucial pre-processing steps, ensuring that each component can process the data efficiently. Integrating multiple NLP components means that their outputs need to be compatible with each other. For example, after tokenization, the output should work seamlessly with part of speech tagging or named entity recognition, otherwise known as NER. Always check that one component's output matches the expected input of the next. Here's a tip to make sure you can follow this best practice. Ensure, through a thorough review of tokenized data, that the now tokenized text maintains the integrity of important entities. For instance, tokenization shouldn't split proper names like New York City into the individual words New, York, and City if you plan to use named entity recognition. The order in which you apply NLP components can significantly affect the outcome. Tokenization should always be the first step, followed by other tasks like POS tagging or sentiment analysis. Sentiment analysis should, ideally, come after POS tagging and NER to provide more context. My tip to you: sequence your NLP components very carefully. Start with tokenization, followed by POS tagging to capture syntax, NER for identifying key entities, and then sentiment analysis to evaluate the emotional tone in the proper context. One of the biggest challenges in NLP is handling ambiguity and context. A word can have different meanings depending on the sentence. And of course, sarcasm can throw off even the most advanced models. Integrating components like POS tagging and NER helps provide context, but you'll need to ensure your models are trained to handle these complex real-world scenarios. Follow this tip to make sure you adhere to this guidance. Use contextual models like transformers, BERT, a great example, which can capture the meaning of words in relation to the entirety of the sentence. This helps your system handle ambiguity and more complex language structures. Finally, testing is crucial when integrating NLP components. Once your system is set up, test it with diverse data sets to ensure it handles different types of language, whether formal text, social media slang, or even domain-specific jargon. So here's a tip to make sure you can incorporate this. Regularly test your NLP system with different data sets and edge cases, like sarcasm or overly technical language. Adjust your models and your pipelines based on performance feedback to ensure they stay accurate and relevant. In this video, we explored best practices for integrating various NLP components to create smooth, accurate systems that process human language effectively. We emphasized the importance of pre-processing, ensuring compatibility between components like tokenization, POS tagging, and sentiment analysis, and of course, sequencing them correctly. We also covered the need to handle context and ambiguity using models like BERT, and the value of continuous testing to refine the system's performance. By following these practices, you can build NLP systems that better understand and generate human language in a variety of applications. Now, take what you've learned and apply it to your own NLP projects. Start by improving your data pre-processing, ensuring component compatibility, and testing different sequences to create a more efficient, accurate system. Remember, good NLP is all about integration. In today's fast-paced world, quick and accurate troubleshooting can make or break customer satisfaction. You've seen how integrating natural language processing, or NLP, into your systems can revolutionize the way you handle support, making it faster and more accurate than ever. You focus on integrating NLP components into systems designed for troubleshooting, improving user interactions, and automating support processes. By the end of this video, you'll be able to summarize the fundamental NLP components used in troubleshooting, such as tokenization, part of speech or POS tagging, and named entity recognition or NER. You'll be able to explain how to build an NLP-driven troubleshooting pipeline that processes user queries and provides relevant solutions. You'll be able to describe real-world applications of NLP in troubleshooting, including customer support chatbots and help desk automation. You'll be able to identify common challenges in integrating NLP into troubleshooting systems, such as handling ambiguity, noisy data, and multilingual processing, and explore solutions to these challenges. You'll also be able to discuss future trends of NLP in troubleshooting, including conversational AI and real-time sentiment analysis. NLP enables systems to interpret human language, making them more efficient at troubleshooting. By integrating these key NLP components, systems can analyze user queries, diagnose issues, and offer solutions faster than ever before. In this module, you focused on how to integrate NLP into troubleshooting systems. Let's start with the core concepts. At the heart of NLP-driven troubleshooting are four essential components. First up, tokenization. This breaks down text into smaller units, or tokens, for analysis. Next is part of speech tagging, or POS tagging, which assigns grammatical roles to these tokens, helping the system understand sentence structure. Next is named entity recognition, or NER, which extracts meaningful information like names, dates, or product names from the text. And sentiment analysis gauges the emotional tone of a user's message, helping systems detect frustration or satisfaction. These components form the backbone of any NLP troubleshooting system. To create a cohesive troubleshooting system, you integrate these components into what we call a pipeline. This pipeline processes user input, transforms raw text into structured data, and enables the system to understand user queries and extract key details. It can also detect user emotions such as frustration or satisfaction. Further, it can identify important entities like error codes, improving troubleshooting accuracy. Taken together, these steps form a powerful tool for diagnosing and ultimately solving issues. NLP has many applications in troubleshooting. You can see it used in customer support chatbots, where bots guide users through diagnostic steps. You can see it in IT troubleshooting systems, which analyze error messages and suggest solutions. You can also see it in help desk automation, where NLP classifies and prioritizes support tickets, allowing help desks to respond more effectively and more efficiently. Each of these applications enhances the speed and accuracy of the troubleshooting process. But, of course, there are challenges when integrating NLP into troubleshooting systems. One of those challenges is ambiguity in language. Words like run, for example, can have multiple meanings. On the one hand, you might be running a race, while on the other hand, run can mean executing a piece of software. By using context-based analysis and named entity recognition, systems can resolve these ambiguities. Another challenge is handling noisy data. User inputs often contain misspellings or slang terms. Robust pre-processing techniques are crucial to clean this data for accurate analysis. Another challenge is found within multilingual systems. Handling multiple languages adds complexity, but pre-trained multilingual models can help manage this challenge. These are just a few of the challenges you addressed in this module. Looking ahead, NLP technologies will continue to evolve, opening new possibilities for troubleshooting. Here are some key trends to watch. First up, conversational AI, where agents will handle more complex queries and engage users in multi-turn conversations. Real-time sentiment analysis is also on the way, allowing systems to monitor user emotions throughout the troubleshooting process. Further, there's also integration with IoT, or Internet of Things devices, enabling real-time diagnostics and predictive maintenance in industries like manufacturing or healthcare. In this module, you learned the integration of natural language processing, or NLP components, into troubleshooting systems, enhancing user interactions, and automating support processes. You learned how to use key NLP components such as tokenization, POS tagging, named entity recognition, or NER, and sentiment analysis to build efficient troubleshooting pipelines. We also examined real-world applications like customer support chatbots, IT troubleshooting systems, and help desk automation while addressing challenges such as ambiguity, noisy data, and multilingual processing. Lastly, we looked ahead at future trends like conversational AI and real-time sentiment analysis. Now that you understand how to integrate NLP into troubleshooting systems, apply these concepts to optimize your own support processes and explore how trends like conversational AI can further enhance your customer service.
Imagine you're a customer frustrated with a malfunctioning laptop and you message a support bot. Within seconds, the bot understands your problem, asks the right questions, and offers a solution. How is this possible? In this video, we'll show you how to build an NLP-powered troubleshooting system that can diagnose and resolve issues automatically. By the end of this video, you'll be able to describe how to combine NLP components like tokenization, part-of-speech or POS tagging, named entity recognition, and sentiment analysis. You'll be able to describe how to apply these components to process user queries and guide the troubleshooting process, and explain how the system handles real-world scenarios and how each NLP task contributes to the overall diagnosis. We begin by setting up our Python environment with the necessary NLP libraries. I will start by creating a new Jupyter notebook. and selecting the kernel with all of our libraries installed. That is Python 3.8, Azure ML. These libraries provide access to a suite of NLP tools from tokenizing text to analyzing sentiment, ensuring our troubleshooting system is well equipped to handle user queries. The first task is tokenization, splitting the text into individual words or tokens. I will copy this code and paste it into my Jupyter notebook, pressing Shift-Enter to run it. This code will be made available for you to copy and paste as well. Here I will import NLTK, and then import word tokenize from nltk.tokenize. Then I will set my text to some sample text. My laptop is overheating after the update, and then we will tokenize the text and print the tokens. However, if you're running this for the first time, you may encounter this error. NLTK says that punct tab is not found. To resolve this error, copy this line, paste it in your Jupyter notebook, and then run all cells from the beginning. Now we see that our sample troubleshooting query has been split into individual tokens. Tokenization breaks the sentence into meaningful units, which we'll analyze further in later steps. Next, we'll apply part-of-speech tagging to identify the grammatical roles of each word. This helps the system understand sentence structure and interpret the relationships between different parts of the query. I'm copying this code and pasting it in my Jupyter notebook, again pressing Shift-Enter to run the code. You may again get another error from NLTK and may need to download more code before you can run this code here. I will copy that line from the error message, paste it here, and press Shift-Enter to run the cell again. Now that we've downloaded the averaged perceptron tagger, we see that the system correctly identifies the part of speech of each word in the sentence. POS tagging helps us understand the grammatical role of each token. For instance, it identifies laptop as a noun and overheating as a verb, helping the system categorize the problem more efficiently. Now, let's identify key entities in the query, such as devices, dates, or product names. Named entity recognition, or NER, allows us to pull out this important information. I am copying this code and pasting it in my Jupyter notebook to run. This code loads a model from Spacey called EN Core Web SM. It adds an entity ruler to the pipeline and then defines two custom patterns. A laptop is labeled as a device and an update is labeled as an event. We then add these patterns to the entity ruler, redefine the sample text, and then calculate the NLP of the sample text. We extract and print these entities here, and we see that a laptop is labeled as a device and an update is labeled as an event. We can ignore this error about NVML because we do not have an NVIDIA GPU attached to our compute instance. By identifying entities like laptop, device, and update event, we provide the system with critical information that helps it narrow down the troubleshooting process. Here, we've manually defined laptop as a device and update as an event. Ideally, you will use an NER model that can recognize the entities you're dealing with. Finally, sentiment analysis will help us understand the emotional tone of the user's query. Is the user frustrated, neutral, or satisfied? This can guide how we prioritize or respond to the issue. I've copied this code and pasted it into the Jupyter Notebook. Here, we initialize a sentiment analysis pipeline from Hugging Face's Transformers library. Then, we analyze the sentiment of the troubleshooting query, which I will now do by pressing Shift-Enter to run the cell. We can ignore these errors about TensorRT and other CUDA errors, again, because we do not have a GPU attached to this system. Here, we see the result. It labels our query as negative with a score of 0.99. Sentiment analysis helps identify whether the user is expressing frustration, which might indicate a more urgent issue that requires immediate attention. Now that all the components are integrated, let's test the system with real-world troubleshooting queries. This will demonstrate how the pipeline works from tokenization to entity recognition and named analysis. Our real-world query was, "My laptop is overheating after the update." We see how that query is tokenized, and then we see the parts of speech of each of those tokens. We also see the different entities in this query, and finally, we see the sentiment analysis of it. Testing the system with real-world queries shows how the system processes the text, extracts key details, and evaluates sentiment to guide the troubleshooting process. In this video, we walked through the process of building an NLP-driven troubleshooting system. By integrating components like tokenization, POS tagging, named entity recognition, and sentiment analysis, we created a system capable of analyzing user queries, extracting key details, and understanding emotional tones. We demonstrated how these techniques can process real-world queries and assist in guiding troubleshooting efficiently and accurately. Now it's your turn. Test the system with additional troubleshooting queries and explore ways to expand its capabilities. Try integrating it with a knowledge base or adding more NLP components to handle complex scenarios. Ever wish you had an AI assistant that could diagnose your tech issues as soon as they happen? Imagine saving hours of troubleshooting time with a smart tool that understands your problem and offers instant solutions. In this video, we're going to show you how to build a basic yet powerful troubleshooting agent using Python. Let's dive in and see how you can create your very own virtual problem solver using natural language processing. By the end of this video, you'll be able to identify key components needed to build a basic troubleshooting agent using Python, explain how to use NLP components like tokenization, part of speech tagging, and named entity recognition, or NER, to process user queries, and describe how to integrate sentiment analysis and decision-making logic to provide effective solutions. Let's start by setting up our Python environment. I will begin by opening a new Jupyter Notebook. And making sure that I have the Python 3.8 Azure ML kernel selected. The libraries in this kernel give us the tools we need to tokenize text, identify entities, and analyze sentiment, all of which are crucial to building our troubleshooting agent. To start, our troubleshooting agent needs to understand what the user is asking. Tokenization is the process of breaking down a sentence into individual words or phrases called tokens. This is an essential step in processing user queries. I will copy this code and paste it into my Jupyter Notebook and run it by pressing Shift-Enter. This code will be made available for you to copy and paste and run in your own environments. Here we have used NLTK to tokenize a sample query. Tokenization breaks down the query into smaller components, making it easier for our agent to understand each part. This step lays the foundation for further analysis. Once we have tokens, we need to understand their grammatical roles. This is where part of speech, or POS tagging, comes in. POS tagging helps us determine if a word is a noun, verb, adjective, or something else, giving more context to each word. Here, we will use NLTK to apply POS tagging to the tokens. Again, I paste the code and press Shift-Enter to execute it. POS tagging helps us know if a word is a noun, verb, or something else. This is useful for understanding the relationship between different parts of the query. Next, we'll use named entity recognition, or NER, to identify crucial entities within the query. This means detecting names of devices, dates, or specific terms that point to the core of the problem. Here, we will use spaCy to apply NER and extract entities. I paste this code and press Shift-Enter to run it. NER identifies important words like John and last Friday to focus the agent's attention on specific details. This is essential for accurate problem diagnosis. A better NER model might also identify entities like the system manufacturer or the user's operating system. We see here that we start by importing the spaCy library. Then we load this pre-trained spaCy model for named entity recognition. We define a sample query different from the last one, which states John purchased a new laptop from Best Buy last Friday. Then we apply the spaCy model to the query to perform named entity recognition. Now, for each entity in doc, we print the entity and the entity label. To improve user experience, our agent can also detect the emotional tone of the query. Sentiment analysis helps identify if the user is frustrated, neutral, or satisfied, allowing the agent to prioritize certain issues. Here, we will use the transformers library to apply sentiment analysis. I paste the code and press Shift-Enter to run it. Here, we initialize a pipeline from the transformers library and set it to a sentiment analysis model. We define a sample query, my laptop is overheating after the last update, and analyze the sentiment of the query. We set the result equal to the sentiment analyzer's analysis of the query and then print it for our inspection. We can see that the label is negative with a score of 0.99. My laptop is overheating after the last update, most likely has negative sentiment associated with it. Sentiment analysis helps the agent prioritize queries where the user is frustrated, ensuring that more urgent cases are handled promptly. Every troubleshooting agent needs a knowledge base to match user issues with appropriate solutions. Let's create a simple dictionary where we map common problems to their solutions. I paste this code and again press Shift-Enter to run it. Here, we have created a dictionary to store common problems and their solutions. We define a knowledge base. We define a function called getSolution. And then we return knowledgebase.get and then the issue name. And then we show an example usage to retrieve a solution for the problem of overheating. We see that our response to having a problem of overheating is to check your cooling system, clean the fans, and ensure proper ventilation. The knowledge base allows the agent to provide quick, predefined solutions, speeding up the troubleshooting process. Our troubleshooting agent should also have decision-making logic to guide the troubleshooting process. If the problem isn't immediately clear, the agent can ask follow-up questions to get more details. I will paste this code and press Shift-Enter to run it. Here, we use conditional logic to guide the troubleshooting process. This conditional logic uses a new troubleshoot function that checks if the query is any of these options, if it is overheating, slow, or purchase. Else it returns, can you provide more details about the issue? The decision-making process enables the agent to identify the problem more accurately or seek additional input when necessary, making the interaction more effective. In this video, you've seen how to build a basic troubleshooting agent using Python. By combining NLP techniques like tokenization, POS tagging, NER, and sentiment analysis with a straightforward knowledge base and decision-making logic, your agent can now understand user queries, diagnose issues, and offer solutions in real time. But this is just the beginning. Consider adding more categories, expanding the knowledge base, or even integrating advanced AI models to create a smarter, more robust system. Try extending this agent by adding more problem categories or integrating it with a larger knowledge base. You can also experiment with more advanced decision-making logic to create an even smarter system. Imagine you have a dataset with hundreds of data points and you need to classify them into distinct categories. How do you transform raw data into actionable insights using machine learning models? In this video, I'll guide you step by step through building and evaluating classification models. By the end of this video, you'll be able to pre-process data for classification tasks, implement and train logistic regression, decision tree, and SVM models, and evaluate the models using performance metrics like accuracy, precision, recall, and F1 score. We'll start by setting up our environment. I'll begin by creating a new Jupyter notebook. And selecting the Python 3.8 Azure ML kernel. We will need a few libraries for this activity: scikit-learn, pandas, matplotlib, and seaborn, which are already installed in the Python 3.8 Azure ML environment. These libraries give us the tools to load and pre-process data, build machine learning models, and visualize results. Now, let's load a dataset into a pandas data frame. After that, we'll explore the dataset to understand its structure and pre-process it for modeling. I will copy this code and paste it into my Jupyter notebook. Then I will press Shift-Enter to run the code and proceed to the next cell. This code will be made available to you to copy and paste into your own environment to run. Here, I have loaded a dataset and explored the structure using pandas. From scikit-learn, we load a dataset on breast cancer. Then, using pandas data frame, we explore the head of the data, showing the first 5 entries in the data frame and the columns, and information about the dataset as a whole. Understanding the dataset helps us determine which features need to be pre-processed. We'll clean the data, handle missing values, and encode any categorical variables before training the models. Next, we'll pre-process the data by handling missing values, encoding categorical features, and splitting the data into training and test sets. I will copy this code, paste it into my Jupyter notebook, and run it using Shift-Enter. Here, we handle missing values and encode categorical variables. We also split the data into training and test sets using train, test, split. df.fillNA handles any missing values, if there are any, in our dataset. Then, we use train, test, split to split the dataset into training and test sets. Pre-processing is essential to ensure that the data is clean and ready for modeling. By splitting the data into training and testing sets, we can evaluate the model's performance on unseen data. Let's start with a simple model, logistic regression. We'll train the model on the training data and evaluate its performance on the test data. I will copy this code and paste it into my Jupyter notebook and run it. Here, we have trained a logistic regression model and calculated its accuracy. We use the logistic regression model from scikit-learn and then use logreg.fit to train the model on our training data. Then, we make predictions and calculate accuracy. We also calculate at this time the precision, recall, and F1 scores of the model, but we will compare those later. Right now, we just want to focus on accuracy, which for the logistic regression model is 95.61%. Logistic regression is one of the simplest models for binary classification, and it's a good starting point to see how well it performs on our dataset. Now, we'll try a more complex model, a decision tree. Decision trees split the data based on feature values and make decisions at each node. I'll copy this code and paste it into my Jupyter notebook and press Shift-Enter to run it. Here, we have trained a decision tree and evaluated its performance. Again, from scikit-learn, we import decision tree classifier and use tree.fit to fit the decision tree classifier model to our training data. Then we use tree.predict to test it on our test data and then calculate the precision, recall, and F1 scores. Again, we are just looking at accuracy for now, and for a decision tree model, it is 94.74%. Decision trees are great for interpretability, but they can be prone to overfitting, as appears to be the case here, where this decision tree is actually less accurate than our logistic regression model. Let's see how it performs compared to logistic regression, 94.74% versus 95.61%. Finally, we'll implement an SVM model, which is great for high-dimensional spaces. SVMs find a hyperplane that separates the data points into different classes with maximum margin. I will paste this code and press Shift-Enter to run it. Here we have trained an SVM model and evaluated its performance. Again, from scikit-learn, we import SVC and then train it on our training data. We then predict the test data and check the actual test data against the data predicted by our SVM model. We see that the accuracy is 94.74%. SVMs are powerful classifiers, especially when the data is not linearly separable. Let's check its accuracy compared to the other models. Its accuracy is exactly the same as that of the decision tree model, but still slightly less than that of our logistic regression model. While accuracy is a good starting point, we can get more insight by evaluating additional metrics like precision, recall, and the F1 score. We can see that for all of these models, the precision, recall, and F1 scores are all 0.96. Accuracy doesn't always tell the full story. Metrics like precision, recall, and F1 score give us a better understanding of how well the model handles imbalanced datasets or specific classes. Perhaps choosing a more complex dataset would reveal the differences between SVMs, decision trees, and logistic regression models. In this video, you are guided through implementing and evaluating 3 common classification models: logistic regression, decision tree, and support vector machine, or SVM. We demonstrated how to pre-process data, train each model, and evaluate their performance using accuracy, precision, recall, and F1 score. By the end, you learned how to compare these models and interpret the results beyond just accuracy, helping you to gain a deeper understanding of model performance in real-world applications. Try running these models on a different dataset, tweak the parameters, and see how the performance changes. It's a great way to deepen your understanding of classification models in machine learning. Imagine a future where machines can make decisions faster and more accurately than any human, predicting trends, solving problems, and driving innovation. Today, I'm going to teach you how to build the decision-making algorithms that are making that future possible. By the end of this video, you'll be able to implement a decision tree model using scikit-learn, evaluate the performance of the decision tree model using accuracy as a metric. To start, we need to set up our environment by installing the required libraries. I will begin by creating a new Jupyter notebook. And then I will select the Python 3.8 Azure ML kernel. This kernel already has installed the libraries that we will need for this activity. These libraries will allow us to load, manipulate, and process the dataset and build our decision-making algorithm. Next, we'll load a dataset into a pandas data frame and explore its structure. This helps us understand what kind of decisions we want our algorithm to make. I have copied and pasted this code into my Jupyter notebook, and now I will run it by pressing Shift and Enter. Here, we load the dataset and explore its structure using pandas. From scikit-learn, we load the iris dataset. Then we print the data frame's head and the data frame's information to show data about this dataset. Here we can see the first 5 items in the dataset, column names, and the values of each item in the dataset for each of those columns. Before we can implement the algorithm, it's important to understand the features and labels in our dataset. This will help guide the decision-making process. We do this by exploring the dataset thoroughly, examining the columns, their data types, and the relationships between features and labels, as well as visualizing data to identify patterns or correlations. For example, we see here that each one of these items is a flower. Measured is the sepal length and width and petal length and width of the flower. The target is a number representing the species of the flower. Before we train the decision-making algorithm, we need to clean the data and split it into training and testing sets. This ensures the model is trained on one portion of the data and evaluated on a separate portion. Data cleaning involves handling missing values by filling them in or removing incomplete entries, removing duplicates, and standardizing data formats to maintain consistency. Once cleaned, the dataset is split on an 80-20 ratio, where a larger portion is used for training the model and the smaller portion for evaluating its performance, ensuring it generalizes well to unseen data. I have pasted this code, and now I will press Shift and Enter to run it. From scikit-learn, we import train test split and use it to split our data into training and test sets. However, first we use df.fillNA to check for any missing values, and if necessary, replace them. We also define features and labels for inclusion in our set. By splitting the data into training and testing sets, we can ensure that our algorithm is not only good at making decisions on the data it has seen, but also performs well on unseen data. Now, let's implement a decision tree algorithm, one of the most common decision-making models. Decision trees split the data into branches based on the most important features, making decisions at each step. I've pasted this code, and now I will press Shift-Enter to run it. Here, we use decision tree classifier from scikit-learn to build and train the decision tree model. As you can see, the model is imported from scikit-learn, and then we use tree.fit to fit the model to our training data. Then we make predictions based on our test data. Decision trees are easy to interpret as they provide a clear path from the root of the tree to the decision leaf. Each node represents a decision based on a feature value, and each leaf represents the final decision. Now that we've implemented the decision tree, it's time to evaluate how well it makes decisions using the test data. We'll calculate accuracy as our main performance metric. Here, we use accuracy score to measure the model's accuracy. We import accuracy score from scikit-learn metrics, and then we calculate and display the accuracy on the predictions we made. We can see here that the accuracy of this decision tree was 100%. Very impressive. Accuracy tells us how often the algorithm makes the correct decision. It's a simple but effective way to gauge the model's performance. If you want to visualize the decision tree, scikit-learn offers tools to help you see how the decisions are made. This can be helpful for understanding the logic behind the algorithm. I've pasted this code and run it using Shift-Enter. From scikit-learn, we import plot tree. We also import matplotlib.pyplot as PLT. Then, we use plt.figure, plot tree, and plt.show to show the decision tree that has been made. Visualizing the decision tree allows you to see how the model splits the data and what decisions are made at each step. In this video, you learned how to implement a decision-making algorithm using Python, specifically through a decision tree. Starting with setting up your Python environment, you loaded and explored a dataset, cleaned and split the data into training and testing sets, and then implemented a decision tree model using scikit-learn. You also evaluated the model's performance using accuracy as a metric. By the end, you had a clear understanding of how decision trees work, making them a powerful tool for decision-making tasks. Now that you've built your own decision-making algorithm using a decision tree, try experimenting with different datasets or tuning the model's parameters to see how it affects performance. Explore more decision-making models and apply what you've learned to solve real-world problems efficiently. Have you ever been stuck troubleshooting the same problem over and over? Today, we'll build a machine learning model that suggests the best solutions for common problems, automating the process and saving you time. By the end of this video, you'll be able to pre-process data for a recommendation system, train a solution recommendation model using the k-nearest neighbors or KNN algorithm, and evaluate the model's performance using accuracy and other metrics. Before we start, let's set up our Python environment. I'll begin by creating a new Jupyter notebook. Then, I'll make sure to select the Python 3.8 AIML kernel. We'll need scikit-learn and pandas for this activity, both of which are already installed in the Python 3.8 AIML kernel. These libraries will allow us to pre-process the data, build the solution recommendation system, and evaluate its performance. Next, we'll load the dataset and explore its structure. This will help us identify problem features and corresponding solutions, which are necessary for training the recommendation model. I will copy this code and paste it into my Jupyter notebook. Then I will press Shift-Enter to run the code. You can see here that we have loaded the dataset into a pandas data frame and explored its contents. Here, we generate an artificial dataset, a synthetic dataset, from these solutions, combining a feature type, a severity, and the solution to the problem. Then, we put this data into a pandas data frame and print data for us to see. Exploring the dataset allows us to understand the structure, including which columns represent the problem description and which columns represent the solutions. Now that we understand the dataset, let's pre-process it. This includes handling missing values and splitting the data into training and testing sets. I'll copy this code and paste it into my Jupyter notebook and run it using Shift-Enter. First, we handle any missing values, though there should not be any in this synthetic dataset. Then, we split the dataset into features and labels, and then split the data into training and testing sets. Pre-processing ensures that the data is clean and split properly into training and testing sets. This step is crucial for evaluating the model on unseen data. Now, we are ready to implement the solution recommendation model using the k-nearest neighbors or KNN algorithm. KNN finds the most similar past problems and recommends solutions based on them. I'll copy this code and press Shift-Enter to run it. From sklearn.neighbors, we'll import the k-neighbors classifier. Then we will use knn.fit to train the k-neighbors classifier algorithm on our training data. Then we will make predictions based on the test data and store them in y_predictions. KNN works by finding the closest neighbors in the dataset to make recommendations based on similar past problems. Next, we'll evaluate how well the recommendation model performs using accuracy. You can also explore additional metrics like precision, recall, or F1 score. Here, we calculate and display the accuracy of our model based on the predictions we made previously. Then we print the model accuracy. We also calculate additional metrics like precision, recall, and F1 score and print them for display. Accuracy tells us how often the model correctly recommends the right solution. If you have an imbalanced dataset, precision and recall can also be valuable metrics. We see here that the recommendation model's accuracy is only 40%, and that is most likely because it is trying to train on and predict to a randomized dataset. Because we used a random selection feature earlier to choose what categories fit into each part of the dataset, to, in other words, make a synthetic dataset with random choices from features and solutions. Our model is not easily able to classify and make decisions and make predictions based on the data we've given it. It would achieve a higher accuracy with a real-world dataset. If you'd like to improve the recommendation model, you can tune the hyperparameters. For example, in KNN, you can adjust the number of neighbors to see if it improves accuracy. Experiment with tuning the number of neighbors and try retraining the model. Tuning hyperparameters like the number of neighbors can improve the model's performance. Finding the optimal settings for your specific dataset is key to building an effective solution recommendation system. In this case, we try improving the model by training it with 5 neighbors. However, this decreases the accuracy from 40% to 35%. Perhaps a different number of neighbors would increase accuracy. In this video, you learned how to build a solution recommendation system using machine learning. You set up your Python environment, explored and pre-processed a dataset, and implemented a recommendation model using the k-nearest neighbors or KNN algorithm. After training the model, you evaluated its performance using accuracy and explored how tuning the model's hyperparameters can further improve its effectiveness. This hands-on approach equipped you with the skills to develop a solution recommendation system that provides relevant suggestions based on past data. Now it's your turn. Use what you learned to experiment with different datasets or tweak the KNN algorithm's parameters to optimize the performance of your recommendation model. Dive deeper into improving your solution recommendation system and see the difference it makes. Errors can occur at any stage of a machine learning pipeline, and tracking them down can be like finding a needle in a haystack. Today, we'll tackle that problem by setting up a logging system that catches every key event, so you'll never be left in the dark. By the end of this video, you'll be able to set up Python's logging module, log key events during data preprocessing, model training, and inference, and log and handle errors to create a robust and maintainable system. First, we'll set up our Python environment. I'll begin by creating a new Jupyter notebook. Then, I'll make sure that I have selected the Python 3.8 Azure ML kernel. Setting up Python's logging system to capture important events is a critical part of the machine learning Python pipeline. We'll store logs in a file so that they can be reviewed later for debugging or performance monitoring. I'll copy this code and paste it into my Jupyter notebook. Then I will press Shift-Enter to run the code and proceed to the next cell. This step configures the logging system to store log messages in the ml_pipeline.log file. We start by logging an informational message to confirm that logging is working as expected. Next, we'll log the key steps in data preprocessing. This includes loading the dataset, handling missing values, and transforming the data. Logging these actions ensures that we can trace how the data is being prepared for the model. Again, I copy the code, paste it, and press Shift-Enter to run the code and proceed to the next cell. Here, we log the start and completion of data loading and pre-processing steps. We make a log when we start loading the iris dataset from scikit-learn, and then we make another log when we have finished loading the dataset. Then we make a log when we start pre-processing the dataset, and then we pre-process the dataset by searching for missing values in the dataset and replacing them if true, and then logging when we have finished checking for missing values and thus finished data preprocessing. Logging each step of data preprocessing helps track how the data is transformed before training the model. This makes it easier to diagnose issues that may arise from improperly processed data. We'll now log the model training process, including the start of training and any relevant metrics such as training accuracy. If errors occur during training, they will be captured and logged. Again, I copy the code, paste it into my Jupyter notebook, and press Shift-Enter to run the code. Here, we log the start and end of model training along with key metrics. Here, we split the data into training and testing sets using scikit-learn's train test split tool. Then we make a log to note the start of model training, and then we try to create a decision tree classifier and fit that decision tree classifier model to our training data. If successful, we output to our log file that the model was trained successfully, else we output to our log file that there is an error during model training and print the exception. Then we check the accuracy of the model and log the training accuracy of the model. By logging the start, completion, and key metrics of model training, you can track how well the model is performing. Any errors that occur during training are captured and logged for debugging. Finally, we'll log the process of making predictions with the trained model. We'll capture inputs, outputs, and any errors that occur during inference. Again, I paste the code and press Shift-Enter to run it. Here, we log the start of the prediction process and capture the outputs. We log the start of the model prediction process, and then we try to make predictions using model.predict and our test set. If successful, we log that the predictions were made successfully, and if not, we log that there is an error making predictions and log the exception. Then we log a sample of the predictions that were made, taking the first 5. Logging predictions provides traceability for the model's outputs, helping you understand how the model behaves in production or testing environments. Logging a sample of the predictions is useful for verifying that the model is working as expected. To view the log that we've made during this test, you can open the file that's been created called mlpipeline.log and see the events that have occurred. In this video, you learned how to implement logging in a machine learning pipeline to improve transparency, debugging, and performance monitoring. You set up Python's logging module and logged important steps during data preprocessing, model training, and predictions. By logging these key events and capturing errors, you now have a clearer view of how your model operates and how to troubleshoot potential issues. This technique is essential for maintaining robust, maintainable machine learning systems. Now that you've seen how to implement logging, add it to your own machine learning projects. Track important events, capture errors, and improve the reliability of your systems. Imagine if your system could detect an issue before you even know it exists, diagnose the root cause, and offer the perfect fix. In this video, we'll build a troubleshooting agent that can do exactly that. By the end of this video, you'll be able to detect anomalies in system logs, implement root cause analysis to identify the source of issues, and create solution recommendations based on diagnosed problems. The first step is to set up our environment. I'll begin by creating a new Jupyter notebook. I'll click on Files, then Create New File, and use the default name. I'll make sure my compute instance is running and that I have selected the Python 3.8 Azure ML kernel. We'll need libraries like pandas for handling data and scikit-learn for building machine learning models. These libraries are essential for building the troubleshooting agent and managing the data pipeline that will power it. Next, we'll load our system logs or performance metrics into a pandas data frame and explore the data. This step is crucial because it helps us understand what kind of issues our troubleshooting agent will be looking for. Here, I paste the code and press Shift-Enter to run the cell and proceed to the next one. This code will be made available for you to copy and paste into your own environment. Here, I have loaded a sample dataset and explored its structure. The dataset we will use here is just a sample one composed entirely of synthetic data. The synthetic data consists of a timestamp, CPU usage number in percentage, memory usage in percentage, network latency in milliseconds, disk I/O in megabytes per second, and an error rate. Then, we use df.head and df.info to display data about the synthetic dataset. Understanding the dataset is key to building a system that can detect anomalies and diagnose problems based on historical data. Once we've explored the data, it's time to implement the anomaly detection system. We'll use the isolation forest algorithm to detect unusual behavior in the system that could indicate a problem. Again, I will paste and press Shift-Enter to run the cell and proceed to the next one. Here, we have implemented the isolation forest algorithm to detect anomalies. First, we define a detect anomalies function, and then we call that function on the numeric data from above. Note that numeric data only consists of floats and ints of columns from our dataset that are of the type either float or int. This excludes the timestamp column. This is necessary to produce accurate results, because timestamp probably has no bearing on errors. We can see here that we have classified the data into 950 non-anomalous rows and 50 anomalous rows. Isolation forest is a great tool for identifying outliers, which in this case represent system anomalies. These anomalies will trigger further diagnostics in our troubleshooting agent. After detecting an anomaly, the next step is to figure out what specific value or values made the log anomalous. Here, we use z-scores to find which columns are anomalous. Again, I will paste, press Shift-Enter, and observe the results. Here, we import z-score from scipy.stats. Then we calculate the z-scores for anonymous values per column. Then we define a function called find_anomalous_columns and apply the function to each row in our dataset that has been marked as anomalous by our forest. Then we display rows with anomalies and their anomalous columns. Here, the agent has identified in which column the anomaly has occurred. This can be an indicator of a problem with, for example, a disk, or the network, or the CPU that needs further troubleshooting and needs to be addressed. In this video, you learned how to build a troubleshooting agent that can automatically detect system anomalies. You set up your Python environment, explored the dataset, and implemented anomaly detection using the isolation forest algorithm. Now it's your turn. Build your own troubleshooting agent and try adding more complex diagnostics and solutions to make it even more robust. Experiment with different datasets and extend the agent's capabilities to handle various system issues.
In the fast-paced world of AI, deploying a model that breaks in the wild can be a costly mistake. Fortunately for us, there's a safety net, the test case. Today, we'll show you how to design test cases that ensure your machine learning model doesn't just perform in theory, but also thrives in practice. By the end of this video, you'll be able to explain the importance of test cases in the machine learning development process. You'll be able to describe the key elements of a well-constructed test case. You'll also be able to describe how to apply test cases to machine learning scenarios to ensure robustness. Test cases are like your system's safety net. They ensure that your model doesn't just work in ideal conditions, like in the lab, but also in less predictable, real-world scenarios. Testing not only helps identify bugs, but it also helps validate how well your model generalizes to new data, catches edge cases, and ensures the robustness of the overall pipeline. Without thorough testing, your model might shine in a controlled environment, but stumble in real-world usage. An effective test case needs to consist of three main components: the input data, the expected output, and of course, the test conditions. Let's break that down a bit further. First up, input data. This can range from typical data your model will encounter to unusual or extreme cases that will challenge its limitations. Next, the expected output. Clearly define what the correct prediction or behavior should be for each case. This helps you know whether your model is behaving as expected. Finally, the test conditions. Consider factors like performance under load, handling edge cases, and ensuring the model can work with either incomplete or noisy data. By having well thought out inputs and expected outputs, you're effectively creating a roadmap that guides your model through potential pitfalls it could face after deployment. Imagine, if you will, a financial company that uses a machine learning model to assess credit risk for personal loans. The model works well for most applicants, handling typical cases of salaried employees with predictable incomes, debt ratios, and credit histories. However, it might struggle with edge cases, like missing data or incorrect formats. Imagine, if you will, one of these applicants, particularly those from underserved populations, may have incomplete financial records. Perhaps their credit history is utterly missing, or their employment data is entered in non-standard formats. The model could miscalculate risk or even reject the application entirely and unfairly. Some extreme values can also cause this aberrant behavior. A high net worth individual might apply for a loan, but their annual income and asset values would be far outside the typical range. The model, trained primarily on middle-income applicants, could wrongly flag this applicant as too risky because it isn't accustomed to these extreme values. Another potential problem would be the unseen category. Say, for example, the company expands into a new region where applicants' employment categories, such as gig economy workers, aren't represented in the original data set. As the model has never seen these categories, it struggles to accurately assess their creditworthiness. Another example might be large data sets. The company experiences a sudden surge in loan applications due to a new marketing campaign, let's say. The increased volume pushes the system's memory limits, causing the model to slow down, crash, or make processing errors for applicants. In each of these situations, the model performs well for typical cases, expected cases, but encounters significant issues with edge cases, demonstrating how critical it is to account for these outliers in our AI system design. Designing test cases to cover these unusual scenarios ensures that your model isn't just good under perfect conditions, but is also resilient enough to handle unexpected real-world inputs. Now, once you have your test cases set up, you'll want to automate their execution. By automating your tests, you ensure that every time you update your model, your test cases run in the background to check for issues. This helps catch bugs early, before they snowball into bigger problems. Automating test execution allows you to continuously validate your model against various test cases, ensuring nothing breaks down when new data is introduced or when model parameters are changed. Testing isn't something you do once and then forget. As your model is deployed, it's important to continuously test and monitor its performance. New data might introduce unexpected behavior, or your model's performance could degrade over time. So setting up continuous testing pipelines and monitoring systems is crucial. By continuously testing and monitoring your model, you ensure that it remains stable and performs well even after deployment. This prevents issues from accumulating and helps maintain model accuracy and ultimately reliability in the long term. In this video, we explore the importance of designing effective test cases for machine learning systems. Test cases help ensure that models perform well not only in ideal conditions, but also in real-world, unpredictable scenarios. We covered the key components of test cases: input data, expected output, and test conditions, along with how to design tests for edge cases and perceived errors. Automating and continuously running test cases are crucial steps for maintaining a robust system that remains accurate and reliable over time. Take the next step by designing test cases for your model. Cover typical scenarios and don't forget about those challenging edge cases. Ensure your model is resilient enough to handle real-world inputs by continuously testing and monitoring its performance.
Imagine releasing a machine learning model into production only to find out it fails on rare, unexpected inputs. Now your system is returning unreliable results, and the pressure is on to figure out what went wrong. In this video, we are going to show you how to design effective test cases that will safeguard your models against such scenarios, ensuring that they handle typical inputs, edge cases, and even errors flawlessly. By the end of this video, you will be able to define test cases for typical machine learning model inputs, create test cases for edge and extreme scenarios, and automate the testing process and validate the model's behavior. Before we start building our test cases, we need to set up the testing environment. I'll begin by creating a new Jupyter notebook. I'll click on Files, and then Create New File. I'll use the default name. Make sure my compute instance is running, and make sure that I've selected the Python 3.8 Azure ML kernel. We'll need to have a framework like PyTest to automate the execution of our test cases. But because we are using Jupyter Notebooks, we will need IPyTest, IPyTest, to run these tests within a Jupyter Notebook. To do so, type !pip install IPyTest. Now press Shift and Enter to run the code and proceed to the next cell. I already have IPyTest installed, so my output may look different from yours. Now, let's create a model. I'm copying this code and pasting it into my Jupyter Notebook. This code will be made available for you to copy and paste as well into your environment. Then I press Shift and Enter to run this cell and proceed to the next one. Here, we've used the iris dataset and a decision tree classifier to create a decision tree classifier model. Now, we'll create test cases that cover the typical scenarios your model is expected to handle. These include common inputs that reflect the data your model has been trained on. I will copy this code, paste it, and press Shift-Enter to run it. Here, we have identified common input data that our model will encounter. And we have also defined the expected behavior of the model. For a classification model, let's say we're classifying types of flowers. We use typical measurements for sepal and petal lengths to check if the model correctly classifies common species. In this case, our model should take these parameters for sepal and petal length and identify it as species 0. Now that we've handled the typical cases, let's push the model to its limits with edge cases. Edge cases are unusual inputs that might stress the model, such as extreme values or missing data. Again, I will copy this code, paste, and press Shift-Enter. Here, we test the model on extreme values, very large numbers, and predict. Then we check to see if a value error is raised for these extremely large inputs, as it should be. This ensures that the model doesn't break or produce incorrect outputs when encountering these rare situations. Next, we need to make sure the model can handle flawed or incomplete data. In this section, we'll create test cases to verify how the model reacts to missing or malformed inputs. I copy the code, paste it, and press Shift-Enter to run. Here, we input test data that contains missing values. Then we check that the model returns an appropriate error message or gracefully handles the input without crashing. If we provide a set of inputs where all values are none, the model should ideally return an error message instead of proceeding with incorrect predictions. After defining all of our test cases, we'll use PyTest to automate the testing process. This ensures that every time the model is updated, we can quickly verify that all tests pass without introducing new issues. I copy the code, paste it, and press Shift-Enter to run it. Here, we use PyTest via IPyTest to automatically run all test cases. Then we monitor the test results to ensure that the model behaves as expected across typical, edge, and error scenarios. Finally, we will review the results of our tests. If the model failed in any scenario, we will refine the test cases or adjust the model to ensure it handles all situations correctly. So, let's review the test outcomes. As you can see, 2 of our test cases failed. It looks like the model doesn't output any errors when asked to predict on very large or indefinite parameters. A solution to this may be wrapping the model in some code that performs input validation to check for invalid data before passing it to the model. In this video, you learned how to design test cases to ensure your machine learning model performs reliably in real-world situations. You walked through setting up a testing environment, creating test cases for typical, edge, and error scenarios, and automating the testing process using PyTest. By the end, you saw how to review and refine your test cases to catch any issues early, helping maintain your model's robustness over time. Now it's your turn. Use these techniques to create and automate test cases for your own machine learning models. By doing so, you'll ensure they're ready to handle typical data, edge cases, and unexpected errors with ease.
Within the employee survey space, I personally designed and implemented tons of surveys. And what we notice over time, of course, is as Gen AI has become much more popular and accessible, you don't have to spend hours and hours analyzing comments anymore. So you can use Gen AI for that for sure. One of my previous organizations, what we did was instead of having people read through the comments, we had built an algorithm to understand what was said in the comments and group them into different themes. We did sentiment analysis and so on. And we started to notice that, again, because it's a large organization, employees may share all kinds of concerns. And we had noticed something very sensitive. For example, perhaps it's behaviors from their manager that may or may not seem very ethical. Perhaps it's mental health concerns or even personal struggles that people decided to share. Because there's no way to control what people fill out in the survey. So the question could ask, what did you have for breakfast? And you could say, you know, I had sausage and egg. Or you could say, I would love to visit Paris, right? So there's no way for the survey designer to really restrict that. So we end up getting all kinds of comments that may or may not be direct response to the question. But we started to notice that there are employee health concerns that we needed to address as an organization. And some of them were so sensitive that we wanted to actually automate and route them to the appropriate teams within the organization. So we could build an automation that route them to, let's say, the compliance team. Maybe it's a health and safety team, depending on the topic. And that seemed very effective for general topics. But what we had discovered is that for cultural context, for example, because it's a large global organization, sometimes it doesn't work well. Sometimes it would pick up a non-concern as a concern and vice versa. So there were cultural issues that was very difficult to address. Not everything can be translated. We also face, of course, language issues. Some people who may respond in multiple languages, right? They may have a mix of English words and something else. And so all those became challenging. The last one that took a little bit of work and we eventually got it to be resolved was acronyms. Right? We had acronyms as a company, so does everyone else. And each region, each business unit may have their own acronym. So we started to include another library, essentially, that help us understand some of those acronyms. So it worked a little bit better for that. But again, we got to a better place. We're able to understand organizational specific acronyms within those survey comments. But for cultural and language specific contexts, it still wasn't a problem that we're able to solve right away. Now, if we were given more time, for sure, with the advancement in other language models, we should be able to do that. But again, I think this is sometimes we think about the volume of comments. How much do you want to spend your time training a model for something that may be very narrow? Let's say you only had 20 employees who might respond in a different language out of 50,000. Is that worth your while? So we think about that trade-off. Maybe we just have humans read those comments instead, right? It's anonymous, as opposed to training a model for that. But then we focus on something that can be used by the large organization, which is understanding acronyms.
Imagine your fraud detection model takes 10 seconds to process a transaction. This would cost your company millions in delayed approvals. What if you could cut that time to milliseconds without sacrificing accuracy? In this video, we'll explore optimization techniques that can transform your model's performance, making it both faster and more efficient. By the end of this video, you'll be able to describe key optimization techniques that improve both model performance and efficiency. You'll also be able to describe how to balance trade-offs between response time and accuracy. Further, you'll be able to explain some practical ways to apply these techniques in real-world machine learning tasks. Optimization isn't just about making your model faster or more accurate. It's also about making the right trade-offs to ensure your model works well in real-world scenarios. Whether you're building a real-time recommendation engine or a fraud detection system, you need to ensure that your model performs efficiently. Every model you create will require fine-tuning to balance between speed and accuracy, especially when working with large data sets or complex algorithms. One of the most effective ways to optimize a model is by reducing its size, a process known as model pruning. Model pruning involves removing parts of the model that contribute minimally to the overall accuracy, such as underutilized neurons in a neural network or unimportant branches within a decision tree. By pruning, you can dramatically reduce the computational load without sacrificing much, if any, accuracy. This speeds up the inference time, making the model faster, particularly useful in environments where quick responses are essential. For example, in a mobile app that uses image recognition, pruning could reduce the model size from 100 megabits to 10 megabits, for example, allowing for faster downloads and smoother performance on user devices. Next up, let's talk about model quantization. Quantization is the process of reducing the precision of the model's weights. For example, instead of using 32-bit floating point integers, you can use 8-bit integers. This drastically reduces the size of the model and speeds up inference time, particularly when deployed on resource-constrained devices like mobile phones or embedded systems. A company develops a mobile app for real-time language translation. The original model, using 32-bit floating point numbers, runs well on high-end devices, but struggles on lower-end smartphones and embedded systems due to limited resources. By applying model quantization, they can reduce the model's weights to 8-bit integers, significantly shrinking its size and ultimately improving its speed. This allows the app to deliver fast, real-time translation across a broader range of devices without compromising too much on translation quality. Another major optimization technique involves feature selection and dimensionality reduction. Often, your dataset contains redundant or irrelevant features that don't contribute much to the accuracy of the model. By eliminating those features, you simplify the model, making it faster to train and more efficient during inference. Techniques like principal component analysis, or PCA, or recursive feature elimination, RFE, help to reduce the number of features, which in turn reduces the complexity of the model while maintaining, or in some cases even improving, its accuracy. Hyperparameter tuning is another powerful optimization technique. The performance of machine learning models often hinges on finding the right hyperparameters, such as the learning rate in a neural network or the number of estimators within a random forest. Using tools like grid search or randomized search, you can explore different hyperparameter combinations to find the ones that yield the best results. While tuning hyperparameters can be time-consuming, it often leads to significant improvements in both accuracy and model efficiency. Leveraging parallel processing and specialized hardware, such as GPUs, can also significantly speed up the training and inference processes. These hardware accelerators allow you to process multiple operations simultaneously, dramatically reducing the time it takes to train deep learning models. For highly complex models, using GPUs can provide the necessary computational power to keep your system fast, even when dealing with large data sets or intricate neural network architectures. Finally, ensemble methods like bagging and boosting help optimize both accuracy and robustness by combining multiple models. Techniques such as random forest or gradient boosting machines aggregate the predictions of multiple models, which often results in more accurate and reliable predictions than any single model could provide. Although ensembles may increase the complexity in the model, they are incredibly powerful for improving accuracy, especially in tasks where precision is paramount. This video explored key optimization techniques that enhance the efficiency and accuracy of machine learning models. We discussed strategies like model pruning, quantization, feature selection, and hyperparameter tuning, which help streamline models for faster performance without sacrificing accuracy. We also highlighted the importance of leveraging hardware optimizations like GPUs and using ensemble methods to improve robustness. These techniques are essential for building models that perform well in real-world applications. Apply one of these optimization techniques, whether it's pruning, quantization, or feature selection on your current model to boost its performance, and see how it affects both speed and accuracy.
Picture this. Your machine learning model works well, but it's slow, resource heavy, and struggles to keep up in real-time scenarios. What if you could make that same model faster, more efficient, and just as accurate? In this video, we're going to show you how to optimize your machine learning model using techniques like pruning, quantization, and hyperparameter tuning, ensuring you get the best performance without compromising reliability. By the end of this video, you'll be able to apply model pruning to reduce model complexity and improve performance, and explain how quantization helps in speeding up inference. To start, let's ensure we have the right environment for the optimization process. I'll begin by creating a new Jupyter notebook. I'll click on Files, then Create New File, then use the default name. I'll make sure my compute instance has started and that I've selected the Python 3.8 Azure ML kernel. We'll be using Python libraries like scikit-learn and TensorFlow to implement these optimization techniques. We'll also need a few other libraries. I'm copying this code and I will paste it here. You will need TensorFlow Model Optimization, which is installed with pip, and tf-keras, which is installed with conda. If this is your first time running this code, uncomment these two hashes so that you will install TensorFlow Model Optimization and tf-keras in your environment. I've already done that, so I'm going to comment out these lines. Then I will press Shift-Enter to proceed to the next cell. Now, let's train a model for use in this activity. Make sure to note the accuracy of the model. We'll compare it to our optimized model at the end. I paste the code, which again will be available for you to copy and paste into your own environment, and then I will press Shift and Enter to proceed to the next cell. Here, we load the MNIST dataset and then build a simple model to train on it. We compile the model, and then we train the model. The total accuracy is 0.97, very high. We'll begin with model pruning, which is the process of removing unnecessary parts of the model, such as underutilized neurons in a neural network or branches in a decision tree, without sacrificing too much accuracy. This helps reduce computational overhead. I copy this code, paste it, and press Shift-Enter to run it. Here, we apply pruning to the model and evaluate the pruned model's accuracy compared to the original. We define our pruning parameters and set our pruned model equal to our original model with the pruning parameters applied. We compile the model, and then we train it on our training data. Then we strip the pruning wrappers to remove pruning-specific layers and metadata. In other words, cleaning up garbage left over from the pruning process. Total accuracy after this pruning and additional training is 0.98. Pruning helps us reduce the size of the model and makes it more efficient without compromising performance too much. This is especially useful for deploying models on resource-constrained devices. Next, let's talk about quantization, a technique used to reduce the precision of the model's parameters. By converting 32-bit floating point numbers to 8-bit integers, we can significantly speed up the inference time. I copy this code, paste it into my notebook, and press Shift-Enter to run it. Here, we convert the model into a TensorFlow Lite model to quantize it. We've converted its 32-bit floating point numbers to 8-bit integers using quantization. Then we evaluate the model's inference time and accuracy after quantization. Quantization reduces the precision of the model's parameters, making it faster, especially when deployed on devices like mobile phones or edge devices without a significant drop in accuracy. Once we've applied all the optimization techniques, we need to evaluate the trade-offs. Did pruning or quantization reduce accuracy too much? Did feature selection improve inference speed without sacrificing performance? Let's review. I paste the code and press Shift-Enter to run it. Here, the quantized model's accuracy, that is the model after it has been pruned and quantized, is 97.91%. Compare this to the original model's accuracy after training, which was 97.65%. We see no loss in accuracy by pruning and quantizing this particular model. If you have access to more powerful hardware, one more technique you can use for model optimization is hyperparameter tuning. You can use a library like GridSearch CV to train your model many different times, each time using different hyperparameters and identifying the parameters that produce the best model. In future activities, we'll also measure the time needed for inference and use that to decide if we have optimized our model using these techniques. In this video, you learned how to optimize a machine learning model using techniques like model pruning, quantization, and hyperparameter tuning. Each method helps reduce complexity and improve efficiency, allowing the model to run faster while maintaining accuracy. By applying these techniques, you can strike the right balance between performance and resource consumption, making your model more efficient for real-world deployment. Now it's your turn to try these optimization strategies on your own models. Try applying pruning, quantization, feature selection, and hyperparameter tuning, and see how much you can boost both the speed and performance of your machine learning models. Imagine your machine learning agent is up and running, making predictions. But how do you really know if it's doing the job efficiently? Is it fast enough? Is it using too many resources? In this video, we'll explore the best methods for evaluating your machine learning agent's performance. We'll walk through the key metrics like accuracy, response time, and resource utilization so you can be sure your model is ready for real-world deployment. By the end of this video, you'll be able to measure the accuracy, precision, and error rate of your agent, evaluate response time and resource utilization for your model, and perform stress testing to gauge scalability. Let's start by creating a new Jupyter notebook. I'll click on Files, then Create New File, and use the default file name. Then I'll make sure that my compute instance is running and that I've selected the Python 3.8 Azure ML kernel. Let's start by training a model we'll evaluate. I'm copying this code and pasting it into my Jupyter notebook, then pressing Shift and Enter to run the code. This is the same model that we have trained in previous versions of this activity. It is trained on the MNIST dataset using TensorFlow. Training takes place over 5 epochs. Now that training has completed, let's measure the accuracy and precision of the agent. Again, I copy this code, which will be made available for you to copy and paste into your own environments, and press Shift-Enter to run the code. We can see that the accuracy is measured at 97%, and the precision is measured at also 98%. Accuracy tells us how often the agent is correct, while precision indicates how relevant those predictions are. Here, we've used a test dataset to compare the agent's predictions to the actual labels. Accuracy and precision are critical metrics that tell us how reliable the agent's outputs are. High accuracy with low precision might indicate that the agent is making too many irrelevant predictions. Next, let's look at response time, how quickly the agent processes input and returns a prediction. For agents in real-time systems, this is an important factor to monitor. Again, I paste code and press Shift-Enter to run. Here, we iterate through this loop 25 times, each time making a prediction. We measure the amount of time it takes to run through all 25 predictions, then divide that time by 25 to get the average time for prediction for this model. We see here that the average response time is 0.4969 seconds. A lower response time is essential for applications like recommendation engines, where delays can affect the user experience. Here, we can track the average time taken by the agent to return predictions. Now let's evaluate how efficiently the agent uses system resources, including CPU and memory. High resource consumption might indicate the need for optimization. I'm copying this code, pasting it, and pressing Shift-Enter to run it. Here, we use psutil to measure the CPU usage and memory usage. Note that, unfortunately, we are not making these measurements while the model is making inferences. So a better measurement may take place when measuring CPU and virtual memory usage when running predictions. You can also see at any time in Azure Machine Learning Studio the CPU usage and memory usage of your compute instance, which roughly aligns with the CPU usage and memory usage of your model, though this can be affected by having other notebooks open at the same time. Efficient resource utilization is key for agents deployed in production environments, especially when handling large data sets or high user traffic. Monitoring this ensures the agent doesn't consume more resources than necessary. Stress testing helps us understand how the agent performs under heavy workloads or with large datasets. We'll simulate those conditions to see if the agent can handle increased demand without performance degradation. Again, I copy the code, paste it, and press Shift-Enter to run. Here, we generate a very large input data, and then we measure the time it takes the agent to operate on that input data and make a prediction. Simulating high volumes of input data or concurrent requests to test the agent's scalability is critical for identifying bottlenecks in the system. By pushing the agent to its limits, we can see whether it can scale effectively or if it needs further optimization. Also note that accuracy and resource usage may change under stress. Here, we see that the total response time, in this case, was 35.9 seconds. In this video, you learned how to effectively evaluate a machine learning agent by measuring critical performance metrics such as accuracy, response time, resource utilization, and scalability. These metrics provide a comprehensive understanding of how well your agent is performing in real-world scenarios. By tracking these factors, you can ensure your model is reliable, efficient, and ready for deployment. Now it's time to put these techniques into practice. Use the evaluation methods discussed in this video to assess your machine learning agents and fine-tune them for optimal performance and scalability.
When you're building AI, you really must consider how your code on the back end flows properly on that front end and how that impacts the user experience. Sometimes when you're designing and building, you find yourself in a funnel where you're thinking specifically about building a particular solution, but you're not really thinking about how somebody's going to interact with that particular solution. It's extremely important to think about your end user and the target audience that you're trying to solve for. For example, I was one time working on a project where we were building a chatbot, and our engineers were working on the code on the back end, and I was testing on the front end. It's extremely important to consider the person that's actually using your chatbot. Now, if I ask a question to that chatbot and the response generation time takes too long, I might think that the chatbot is broken or that there's issues, and I may exit the chatbot. It's important that when you are working on your response generation time, that you provide your end user with a visual indicator to let them know that the answer is coming soon and to hold on tight. Think about your own personal experiences using your phone, your computer, or even a website. If it's taking too long, you force quit and you exit. Another example that you may want to consider is the intent of the question that you're trying to get answered. If I, as the end user, am coming in to ask a question to the chatbot, and you take too long to understand the question that I'm asking, I also might exit and leave the experience. It's really important to consider the funnel of all the interactions from an end user standpoint and how many times you ask them to interact or to answer a clarifying question to get them closer to that end answer. Think about your flow and think about the different channels that you may need to pull triggers on in order to then get them to that right answer at the end. And also think about what's the actual end exit point when you know that that bot may not actually answer the question for the user. It may be you giving them a phone number to reach out to, a ticket to submit to, or an additional resource like a PDF or a website URL if you know that your bot just can't answer that question. It's important to keep your end user in mind because you want them to be interactive, you want them to be interested, you want them to be engaged, and most importantly, you want them to come back and interact with your chatbot again.
Imagine you're deploying an AI-powered customer service agent, and it's handling thousands of inquiries per minute. But what happens when it starts slowing down or giving inaccurate responses? In this video, we'll dive into the critical process of testing and optimizing a machine learning agent, ensuring it remains fast, accurate, and efficient under pressure. By the end, you'll know exactly how to fine-tune your agent to perform reliably in real-world scenarios, balancing power and speed to keep up with growing demand. Because you've completed this module, you should now be able to identify key performance metrics, such as accuracy, precision, response time, and resource utilization for testing machine learning agents. You should understand optimization techniques including model pruning, quantization, feature selection, and hyperparameter tuning. You should be able to apply evaluation strategies like benchmarking, A/B testing, cross-validation, and stress testing to assess the agent's performance. You should be able to balance trade-offs between performance and efficiency to ensure the agent meets real-world application requirements. Further, you should be able to recognize the importance of continuous monitoring and improvement after deployment to maintain the agent's performance over time. When testing your agent, it's crucial to focus on a few key performance metrics. First up, accuracy and precision. These measure how well your agent makes correct and relevant predictions. Response time, the time it takes for your agent to process inputs and return results, which is critical in real-time applications. Resource utilization. You'll need to monitor how efficiently your agent uses system resources like CPU, memory, and network bandwidth, especially under high-load conditions. Scalability. Can your agent handle increasing data volumes or requests without performance degradation? Error rate. Keeping track of how often your agent makes incorrect predictions will help you identify areas for improvement. Once you've tested your agent, it's time to optimize its performance. Let's take a look at some key optimization techniques. Model pruning. This reduces the model size by removing unnecessary components, improving speed and efficiency. Model quantization. By lowering the precision of your model's parameters, you can significantly speed up inference without sacrificing too much in accuracy. Feature selection. Removing irrelevant features simplifies your model, making it faster and more efficient. Hyperparameter tuning. Adjusting settings like learning rate or the number of layers can improve both accuracy and response time. These techniques allow you to fine-tune your agent for optimal performance. Several testing methods can help you evaluate your agent's performance, like benchmarking, for example. This is comparing your agent to industry standards or other models in order to provide insight into its effectiveness. A/B testing. Running two versions of your agent allows you to assess the impact of specific changes to one of the versions. Cross-validation. This ensures your agent performs consistently across different data subsets, which helps prevent overfitting. Stress testing. Testing under extreme conditions helps you identify performance bottlenecks and ensure scalability. These strategies help ensure your agent is ready for real-world demands. When optimizing your machine learning agent, you'll often face trade-offs between performance metrics. Accuracy and response time are a great example. Improving accuracy can increase computational costs and slow response times, while simplifying the model can reduce accuracy, but of course, speed things up. You'll be faced with resource utilization and scalability. As resource demands grow, optimizing how your agent handles those resources is essential for maintaining scalability. In some applications, like real-time systems, response times, well, they may be prioritized over accuracy. In others, such as medical diagnoses, accuracy is critical, and higher resource consumption may be acceptable. Once your agent is deployed, continuous monitoring is crucial to maintain its performance. By tracking metrics like accuracy, response time, and resource utilization, you can detect and address performance issues early. Regular retraining ensures your agent adapts to changes in data or changes in user behavior, keeping it effective and relevant over time. In this module, you learned how to test and optimize a machine learning agent for real-world applications, focusing on key performance metrics like accuracy, response time, and resource utilization. You also explored optimization techniques such as model pruning, quantization, and hyperparameter tuning to improve the agent's efficiency. Additionally, we discussed testing methods like benchmarking, A/B testing, cross-validation, and stress testing, all of which are essential for ensuring the agent's performance and scalability in demanding environments. Now that you've seen how to test and optimize your machine learning agent, apply these techniques to fine-tune your own models. Make sure to continuously monitor performance and keep your agent scalable and efficient even as those demands increase.
Imagine you've built a machine learning agent for a real-time fraud detection system at a large financial institution. In the controlled environment of your lab, the model is performing well, flagging suspicious transactions with impressive accuracy. But in the real world, thousands of transactions are processed every second. Can your model keep up? In this video, we'll explore how to rigorously test and optimize your agent, ensuring it not only maintains accuracy under heavy load, but also responds quickly enough to prevent fraud in real time. By the end of this video, you'll be able to measure the accuracy, precision, and response time of a machine learning agent, apply pruning and quantization to optimize performance, and conduct stress testing and balance the trade-offs between accuracy and speed. I'll start by creating a new Jupyter notebook. I will leave the default file name. Make sure that my compute instance has started, and make sure that I've selected the Python 3.8 Azure ML kernel. We will start by training a model. I am copying and pasting this code into my notebook and pressing Shift-Enter to run it. Once the model has finished training, we will prune it. Again, I copy and paste this code. And then we will quantize it. Specific details about the training process and the pruning process and the quantization process can be found in other parts of this course. We'll start by measuring accuracy and precision, two of the most critical metrics for evaluating a machine learning agent's performance. Accuracy tells us how often the agent's predictions are correct, while precision measures how relevant those predictions are. I copy this code, which again will be made available for you to copy and paste into your own environments, and press Shift-Enter to run it. Here we see that the model accuracy is 97.9% and the model precision is 97.9%. This is in line with the precision and accuracy of the unoptimized model we covered in a previous video. Next, we'll measure the agent's response time, how quickly it processes inputs and returns predictions. For real-time systems, such as recommendation engines, this metric is crucial. Again, I copy this code, paste it, and press Shift-Enter to run it. Here, we see that the average response time is significantly lower than it was with the unoptimized model. The unoptimized model took an average of 0.49 seconds per response. Here, it is only 0.0001 seconds. This is a benefit of quantization and pruning. Now, we'll look at how efficiently the agent uses system resources like CPU and memory. High resource usage can indicate that the agent needs optimization. Again, these metrics are imperfect because they are not being measured while inference is being run. However, we can examine CPU usage and memory usage while inference is being run and use it to estimate how much memory our model and how much CPU our model is using. By optimizing resource utilization, we ensure that the agent can scale effectively even under high loads. The memory utilization of this quantized model will be less than that of the unoptimized model. Let's now perform stress testing to evaluate how the agent handles high data volumes and concurrent requests. Stress testing allows us to assess the scalability of the agent under extreme conditions. Again, I paste the code and press Shift-Enter to run it. Here, we generate a very large input set, then log the start time, and then perform inference on that large input data. Then we log the end time and take the difference of the end time and the start time to find out how long it took the model to respond to this stress test. We see that the unoptimized model took between 20 and 40 seconds to complete the stress test. The optimized model completes it in 18 seconds. Finally, let's evaluate the trade-offs between accuracy and response time. With the optimization methods that we've put in place here, we've seen only a 1 percentage point decrease in accuracy while majorly decreasing resource usage and response time. Finding the right balance between accuracy and speed ensures the agent is optimized for its specific application, whether it prioritizes real-time results or high predictive accuracy. Here, accuracy has remained roughly the same, but resource usage has decreased and speed has increased. In this video, you learned how to rigorously test and optimize a machine learning agent for real-time applications such as fraud detection. You learned how to measure critical performance metrics like accuracy, precision, response time, and resource utilization. You also applied optimization techniques, including model pruning and quantization, to improve efficiency without sacrificing accuracy. Finally, stress testing helped evaluate the agent's scalability under high loads, and you analyzed the trade-offs between accuracy and speed to find the optimal balance for real-world performance. Now that you've seen how to test and optimize your machine learning agent, try applying these techniques to your own models. Measure and monitor performance, apply pruning and quantization for better efficiency, and stress test your agent to ensure it can handle real-world demands. Balancing accuracy and speed will ensure your agent performs reliably, even under pressure.
Sometimes in my career, I don't just get to build AI and ML models, I get to implement them. And one example I will share that I got to partner with a vendor as we're rolling out something called an internal talent market place. So it's a fancy name for a tool that would essentially provide recommendations for different jobs, who might be the top candidate. So it will go through resumes from external candidates along with the profiles of our employees internally. And then it will give it, kind of 1, 2, 3, 4, 5-star rating, depending on the matching. Now, the matching is based on a large number of factors. The vendor had said this is one of the ways that we help organizations improve their diversity. It actually should remove the bias from the hiring process. What it does is it focuses on the skill set, it focuses on the experience, and instead of caring about where a person went to school, whether or not they worked at prestigious employers before, you really focus on what they're able to do. Sounds like magic. As we're doing the implementation, actually prior to implementation, we did a testing. So we picked out 3 different roles, and we fed in thousands of resumes that we really have, including internal candidates. And it seems to be doing an okay job picking out good candidates. We, had recruiters also jump into the testing process and ask, would you select this candidate for the interview as validation? We included some hiring managers as well for the process. All seems great, except we noticed something strange. Now, the process actually removes the names from the resume. So if you want to look it up as a hiring manager, you can, but it's not the first thing you see on the resume, like a normal resume. So you really see the matching, and then you can dig into their qualifications. Again, great for improving diversity. What we noticed was that the top candidates that this AI tool picked out, look very similar to our current leadership team. So they share similar schools as far as college and grad school. They look very similar in terms of demographics. So yes, I'm talking about gender and race. And there was no point of time when we told this AI tool that please pick out similar candidates that resemble our leadership team. But it was doing that on its own for some reason. So at this point, I called the vendor and said, hey, it seems to be doing the opposite of what you promised, which is improving diversity. It's picking out people who essentially look the same as what we already have. And they assured us, no, we have gone through lots of implementation with companies just like yours, and it has improved diversity for X%. I said, well, that might be great for other places. The fact is, it's not doing that using our data. So only going back and forth, we finally found that somewhere within the code that this AI tool had made the assumption that successful candidates are our leadership team. And again, it was one of the weird default settings that we didn't know. And the vendor didn't ask us if we wanted to select it. And so once we were able to solve this mystery, of course, we paused the implementation for a bit because it's not ready for prime time. And once we figured this out, at this point, our legal team got very concerned. They said, well, it looks like it might be increasing the bias instead of removing the bias. And we need to do something around that. So during that time, we started to set up an entire new process on how we are going to monitor what this AI tool is doing and will be doing going forward. So we set up a regular review on the candidates the AI tool is selecting and comparing that to our current demographic. And then we have the legal team involved in all these process to make sure that, they share with us as well the latest regulations that we need to be mindful of, because this, of course, constantly changing, along with privacy rules. And that's how we eventually were able to get to the finish line, along with a new process set up to validate whether or not this AI tool is doing what it's promised to do.
Imagine your agent is deployed in a busy production environment. Thousands of users rely on it to make quick, accurate predictions. Is it ready? In this recap, we'll cover the key testing and optimization techniques that will give you confidence your agent can handle the pressure. Throughout this course, you've learned how to evaluate a machine learning agent's performance using key metrics such as accuracy, precision, response time, and resource utilization. You've learned how to apply optimization techniques like model pruning, quantization, and feature selection to improve your agent's efficiency. You've learned the importance of conducting stress testing to assess scalability and manage trade-offs between accuracy and speed. You've also learned it's necessary to continuously monitor agent performance and ensure long-term effectiveness in real-world applications. In the early part of the course, we focused on evaluating the performance of machine learning agents. By measuring key metrics like accuracy and precision, you learned how to assess the quality of your agent's predictions. Response time and resource utilization were critical for ensuring the agent was efficient and scalable in a production environment. Remember, these metrics are the foundation for understanding how well your agent performs. Without accurate and timely predictions, the agent won't be reliable for those real-world applications. Next, we dove into optimization techniques. You learned how to use model pruning to reduce model complexity and quantization to speed up inference by lowering precision. We also covered feature selection, which helps simplify the model by focusing only on the most relevant features. These techniques not only make your agent faster, but also more efficient, allowing it to scale better and operate on resource-constrained devices. We then explored the importance of stress testing, putting your agent under heavy loads to see how well it scales. Understanding the trade-offs between accuracy and response time was crucial for balancing performance with speed, ensuring your agent remains effective even under pressure. Stress testing helps you identify bottlenecks before they become issues in production, giving you the confidence that your agent can handle those real-world workloads. Finally, we discussed the need for continuous monitoring and retraining. Machine learning agents need to adapt to changes in data and in environments. By monitoring performance in real time and retraining your models regularly, you can maintain their effectiveness over time. Continuous improvement is key. The real world changes, so should your agent. Regularly retraining your models ensures that your agent will stay relevant and, of course, effective. In this course, you learned how to evaluate and optimize machine learning agents for real-world applications. You learned to assess performance using metrics like accuracy, precision, and response time, and applied optimization techniques such as model pruning and quantization to improve efficiency. You also learned to use stress testing to ensure scalability and the importance of continuous monitoring and retraining to keep agents effective over time. Now, put these lessons into practice by testing, optimizing, and continuously monitoring your machine learning agents to ensure they're performing at their best in real-world scenarios.
Picture this. You're creating powerful AI solutions in Microsoft Machine Learning Studio, but you have a problem with your deployment. How do you resolve it? You can build your own personal troubleshooting agent to help you with these problems. By the end of this video, you'll be able to navigate to and demonstrate proficiency with Azure deployments for an LLM-based troubleshooting agent, and deploy an LLM-based troubleshooting agent using serverless endpoints. First, let's navigate to Azure Machine Learning Studio. If you haven't already, go to ml.azure.com in your web browser and sign into your Azure account. Now, under Assets, click on Endpoints. Then click on Serverless Endpoints. Let's create a new serverless endpoint by clicking the Create button. Now, I'll search for a model. For this demonstration, I'll use Llama 2 70B Chat as my base large language model. I click the checkbox next to the model, then click Select. I'll click on Pricing and Terms to briefly review the pricing for this model. We can see that the cost is approximately 0.2 of a cent for each 1,000 tokens input to this model, and approximately 0.2 of a cent for each 1,000 tokens output from this model. Very affordable. Now, click Continue to deploy. We'll disable the content filter and give our deployment a custom name. Let's call it LLM-based troubleshooting agent. It seems that I need an agent to help me troubleshoot my spelling. Then we'll click Deploy. This next step may take a couple minutes. Wait until the provisioning state and endpoint state have finished creating. Now that the provisioning state and endpoint state have succeeded, click the Test tab. Here, we can review the model and send input to the model for it to run inference on. This is an example prompt for a troubleshooting agent in a large language model. This will be made available for you to copy and paste into your own LLM. I'll paste it here and press Enter. Now, I can describe my issue to the troubleshooting agent. For example, I need help creating a new compute instance in Azure Machine Learning Studio. And the troubleshooting agent will provide the steps needed to create a new compute instance in Azure Machine Learning Studio. And there you have it. Deploying, customizing, and testing a model in Azure Machine Learning Studio is that straightforward. Now you're ready to bring your AI models to life and explore their full potential. In this video, you learned how to create a troubleshooting agent using a large language model deployed on a serverless endpoint in Microsoft Azure. Now it's your turn. Try experimenting with different models and prompts to create the best troubleshooting agent for your task.
Two machine learning agents enter production. One falters under pressure while the other thrives. What's the difference? Well, the difference is the optimization techniques you've learned in this course. Let's take a moment here to celebrate your accomplishment and reflect on the skills that will set your models apart. Throughout this course, you've gained essential skills for testing and optimizing machine learning agents. From evaluating performance metrics like accuracy and response time to applying optimization techniques like model pruning and quantization, you've seen how to make a machine learning model both efficient and effective. These techniques are the foundation of making models work in real-world environments, where speed, efficiency, and scalability matter just as much as accuracy. You've also learned how to apply these skills in practical contexts. Whether it's optimizing a recommendation engine, developing a real-time image classifier, or building an NLP-based chatbot, the knowledge you've gained will help you approach new machine learning challenges with confidence. Machine learning isn't just about building models. It's about optimizing them to be useful in real-world applications, and you now have the skills to do exactly that. So what's next? The field of machine learning is evolving fast, and there's always more to learn. You can apply these optimization techniques to your own projects, explore more advanced topics like hyperparameter tuning or model deployment, or even start working toward becoming an AI ML specialist. The key to mastering machine learning is continuous learning and applying your knowledge in real projects. There's always something new to discover, and you're now well equipped to take the next step. If you're not already enrolled, consider continuing the Microsoft AI and ML Engineering Professional Certificate. Course 4 provides hands-on experience with Microsoft Azure's AI and ML services. Course 5 explores advanced AI and ML techniques and includes a comprehensive capstone project. I want to congratulate you again on completing this course on testing and optimizing machine learning agents. You've gained valuable skills from evaluating performance metrics to applying optimization techniques like pruning and quantization. These are key elements to making models efficient and scalable for real-world applications. Now that you've completed the course, take the next step by applying these techniques to your own projects, exploring advanced topics, or continuously improving your own skills in machine learning. Keep experimenting, keep optimizing, and keep pushing your knowledge even further.